There is an object spinning through the solar system, yet from Earth, no one can see the full extent of that rotation. It is too small to appear as a world with a clearly defined outline, too distant for its craters, rocky slopes, or irregular surface features to be distinguished. Through telescopes, all that remains is a faint point of light, sometimes slightly brighter, sometimes dimmer, as though the object were slowly sending a signal back to Earth that no one had yet been able to fully decode. That point of light is called Donaldjohanson. Welcome to Night Cosmos Sleep. On tonight's journey, we will gradually approach a small asteroid located between Mars and Jupiter, where two rocky masses are joined together in a shape resembling a peanut, tumbling through space with two different rhythms of motion. But before the Lucy spacecraft came close enough to reveal its true shape, Donaldjohanson existed in the data only as a point of light that changed very slowly against the darkness. Between the orbits of Mars and Jupiter lies a region commonly known as the main asteroid belt. The name can easily bring to mind an image of thousands of rocks packed closely together, forcing a spacecraft to weave constantly between them to avoid collisions. But the reality is almost the opposite. This is an immense region of space in which objects are usually separated by enormous distances. A spacecraft can travel through the belt and, for most of the journey, still see nothing but darkness. The asteroids do not form a wall of rock around the sundae. They move along their own individual orbits, scattered across a region hundreds of millions of kilometers wide. Even if you were standing on one of them, the nearest objects might still be too distant to see with the naked eye. Donaldjohanson travels through this emptiness as a very small member of an ancient population. It completes its orbit around the Sun between the two planets, receiving light from the central star and reflecting a tiny fraction of it back into space. The asteroid belt is often considered to be material left over from the formation of the solar system. About 4.5 billion years ago, the young Sun was surrounded by a vast disk of gas and dust. Small particles of matter collided, stuck together, and gradually formed larger bodies. In many regions, this process continued until planets emerged. But in the region between Mars and Jupiter, that process of accumulation was never completed. Jupiter's powerful gravity repeatedly disturbed the motion of the surrounding material. Their orbits were pulled out of alignment, collisions became more violent, and the formation of a large planet became increasingly difficult. What remained was a diverse collection of rock, metal, and carbon-rich material. Some objects are hundreds of kilometers across. Many others are far smaller, little more than irregular masses of rock carrying the scars of countless collisions. Donaldjohanson belongs to this smaller group. Its greatest length is about 8 kilometers. On the scale of human life, that is still a considerable distance. But compared with planets or large moons, it is only a very modest fragment of material. Its small size also means that Donaldjohanson has extremely weak gravity. A large planet has enough mass to pull its material toward the center, gradually shaping the entire body into something close to a sphere. That is why Earth, Mars, and many large moons are relatively round, even though their surfaces still contain mountains and valleys. Donaldjohanson does not have enough gravity to do this. Its protruding regions are not pulled completely downward. Steep slopes, rocky ridges, and asymmetrical features can remain in place for extremely long periods. The object is free to preserve the shape created by collisions and accumulation processes in its distant past. Before Lucy's flyby, however, that shape remained beyond the reach of direct observation from Earth. The asteroid was too small and too far away for telescopes to distinguish individual features on its surface. Sunlight struck it and scattered in many directions, but only a tiny fraction traveled the long distance back to our observing instruments. Even powerful telescopes recorded Donaldjohanson only as a point of light. There was no narrow neck connecting two rocky masses, no visible outlines of craters, no direct indication that one end was larger than the other. But a point of light is not completely silent. As astronomers observed Donaldjohanson over many nights, they noticed that its brightness changed. At times, the point of light became slightly brighter. Then it dimmed before gradually returning to its previous brightness. These changes happened slowly and repeated in a relatively steady rhythm. The reason was not that the asteroid produced its own light. Donaldjohanson only reflected sunlight. What changed was the portion of its surface facing the observer. An object that is nearly spherical may reflect a relatively stable amount of light as it rotates, but an elongated or asymmetrical mass of rock behaves differently. When its broader side faces Earth, a larger area receives and reflects sunlight. When its narrower side turns toward us, the point of light becomes dimmer. By recording these changes, astronomers create what is known as a light curve. It is a record showing how an object's brightness rises and falls over time. From the repeating pattern of that curve, they can infer part of the object's motion without ever seeing its true shape. Observations from Earth showed that Donaldjohanson's brightness repeated in a cycle of about 10.5 days. Compared with many asteroids that complete a rotation in only a few hours, this was an extremely slow rhythm. For a long time, the 10.5-day cycle was considered the most important clue to the object's motion. It seemed to suggest that Donaldjohanson needed more than 10 days to complete a single rotation. Those observations were not wrong. The telescopes had accurately recorded a real rhythm present in the reflected light, but the enormous distance allowed them to see only part of the motion. It is similar to watching a rotating object from far away. We may notice when its broad side and narrow side alternately turn toward us. Yet from changes in brightness alone, it is very difficult to determine whether the entire object is also tilting sideways, rocking around another axis, or flipping end over end as it rotates. Donaldjohanson therefore kept most of its secrets. The point of light did not reveal that the object was made of two large rocky masses joined together. It did not show how its slopes had changed over time, nor did it reveal that the 10.5-day cycle was only one part of a far more complex motion. From Earth, the asteroid still appeared simple and distant. A faint point of light, slowly brightening and dimming within the nearly empty expanse of the main asteroid belt. But as Lucy moved closer, that point of light did more than grow larger. It began to move with a rhythm that distant observations had never been able to see. In the earliest images from the final 2 hours of approach, Donaldjohanson still did not resemble a world. It occupied only a few tiny pixels against the black background, appearing as a faint gray patch that was not yet clear enough to distinguish rocky slopes from craters, or even to tell exactly where its true outline ended. Without knowing its coordinates in advance, it would have been easy to mistake that point of light for a distant star behind it. But Donaldjohanson was not fixed among the stars. It was orbiting the Sun, while the Lucy spacecraft was rapidly approaching the point where their paths would pass close to one another. On the 20th of April 2025, the distance between Lucy and the asteroid began to close quickly. The spacecraft was not arriving to land, nor was it slowing down to enter orbit around Donaldjohanson. This was only a flyby, a brief encounter in which both objects would continue along their own separate paths. That meant every observation had to take place within a limited window of time. A spacecraft in orbit can revisit the same region many times, return to places it missed, and observe the surface under different lighting conditions. Lucy would not have that opportunity. After the moment of closest approach, the distance would begin increasing again, and Donaldjohanson would gradually shrink in the field of view until it returned to being a point of light once more. About 2 hours before the flyby, the asteroid was still more than 93,000 kilometers from Lucy. At that distance, it remained a small shape, but it was no longer completely undefined. Each new image showed the object growing slightly larger. Pixels that had once blended together began to form an outline, although that outline was still faint and seemed to shift easily with the viewing angle. Donaldjohanson itself was not growing. The distance between it and the spacecraft was rapidly disappearing. Lucy and the asteroid passed one another at a relative speed of about 48,000 kilometers per hour. At that speed, the spacecraft could travel a distance equal to Earth's circumference in less than an hour. But in space, this motion produced no rushing sound, no powerful wind, and no trail of fire, like an object moving through an atmosphere. Lucy simply traveled silently through the vacuum, while the image of its target continuously changed inside its observing instruments. As the distance fell to several tens of thousands of kilometers, the point of light began to stretch. One side appeared broader, while the other narrowed, but the shape was still not clear enough to determine whether it was merely one elongated rock or something more complex. The images were not simply recording the same viewing angle at different sizes. As Lucy moved, the relative positions of the spacecraft, the asteroid, and the sun changed continuously. Light fell across different slopes in turn, gradually revealing regions that had previously been hidden in darkness, while other areas slipped out of view. Each image therefore preserved a different slice of the object. A projection that appeared only faintly in one image might become clearer in the next. A dark region did not merely show where less light was reaching the surface. It could also reveal the angle of a slope or the location of a deep depression. By arranging the images in chronological order and comparing them, scientists could track the changing outline and gradually reconstruct the three-dimensional shape of Donaldjohanson. The process was not like taking a single photograph and immediately seeing every detail. It was more like walking around an object in a dark room while a single beam of light illuminated it from one direction at a time. Every viewing angle was missing something, but once enough slices were assembled, the overall structure began to emerge. The distance continued to fall, and the asteroid was no longer merely an isolated point of light. Its dark gray surface occupied more of the frame. Areas of light and shadow became more distinct, and several craters began to appear as incomplete circles. Rocky slopes descended into lower regions. Ridges crossed the surface before being interrupted by impact depressions. Donaldjohanson gradually became a landscape with a structure of its own. For the first time, humanity could see the object as a real world, rather than merely a point of light represented by numbers in a dataset. While visible light images recorded the outline and surface details, infrared observations provided additional information about the material, making up the outer rocky layer. Minerals do not respond to every wavelength of light in the same way. They absorb certain portions and reflect others, producing distinctive patterns that help scientists infer their composition. Yet during the brief encounter, no one could immediately read the entire story contained in the incoming data. The images and spectra had to be transmitted back to Earth, processed, compared, and assembled. An encounter lasting only a short time could still produce months or even years of analysis afterward. Lucy continued rushing forward, and the outline of Donaldjohanson became increasingly unusual. The object did not taper evenly like a single mass of rock. A larger section appeared on one side, while the remaining section seemed to be attached through a narrower region. Even so, the asteroid's own motion prevented this shape from appearing fully in every image. Donaldjohanson was tumbling as Lucy approached, so the viewing angle changed not only because the spacecraft was moving, but also because the entire object was rotating and tilting in several directions. At times, one section blocked the other. At other moments, shadow made the connecting region difficult to recognize. Only when the images were arranged correctly according to time and viewing angle did the two-part structure begin to become clear. At closest approach, Lucy passed only about 1,000 kilometers above the surface. On Earth, that would be the distance between two cities, but for a spacecraft, sweeping past an object only about 8 kilometers long at tremendous speed, the clearest observing window still passed quickly. Donaldjohanson expanded within the field of view, reached its largest apparent size, and then began to shrink again. There was no moment when the spacecraft stopped beside it for another look. There was no return orbit around the opposite side. Lucy continued straight along its calculated trajectory, heading toward more distant targets near the orbit of Jupiter. The encounter with Donaldjohanson had originally been selected partly as a dress rehearsal. Lucy's primary mission is to study the Trojan asteroids, objects that orbit the Sun near Jupiter's path. Before reaching them, this flyby allowed the mission team to test the spacecraft's ability to track a small moving target, keep its instruments pointed in the correct direction, and collect data during a brief approach. Donaldjohanson might therefore have been viewed as little more than a stop along a much longer journey, but the images it produced quickly showed that it was not simply a target for testing equipment. The object's shape was more complex than expected. Its motion contained a rhythm that had never been fully observed from Earth. Its surface carried craters with unusual outlines, while its mineral composition may preserve traces of water from an older parent body. An object that had once appeared only as a point of light had become a scientific story of its own. After the flyby, the distance between Lucy and Donaldjohanson began increasing again. The asteroid gradually shrank in the final images. Its craters disappeared first, its slopes blended together, and its two-part outline contracted into a small shape before eventually returning to only a few bright pixels within the darkness. But this time, that point of light was no longer entirely unknown. Lucy had seen it from enough angles for scientists to begin assembling its true shape. And when the clearest images were placed beside one another, Donaldjohanson did not resemble a single mass of rock. It looked like two worlds that had once found each other. In the clearest images captured by Lucy, a large rocky mass appears first, occupying most of the field of view. Behind it lies a smaller section, neither completely separate nor smoothly blended into the larger body along an even curve. Between the two is a narrow region of material, like a neck of stone holding them together in space. From certain angles, Donaldjohanson's outline makes it look almost like a giant peanut. The two ends bulge outward while the middle narrows, but that comparison offers only a quick impression of its overall form. As the object turns to another angle, the asymmetry becomes more apparent. One lobe is larger and fuller, while the other is smaller, with a distinct outline, and seems to be attached to the larger section at a slight offset. Donaldjohanson does not have the symmetry of an object that formed around a single center. It resembles two rocky bodies with separate histories that were later brought together and preserved within the same structure. Scientists describe this as a bilobed shape. A lobe is a large, relatively distinct section of an object. When two lobes exist together and are connected by a narrow region, the body may be described as a contact structure. This does not necessarily mean there is a perfect boundary between the two masses inside. Material in the connecting region may have been compressed, shifted, or accumulated over time. But the external shape still shows that the two major sections are not identical and may once have existed as separate fragments. The surfaces of both lobes are far from smooth. Low-angle sunlight falls across the rocky slopes, revealing alternating regions of light and shadow. There are craters formed when smaller objects struck the surface. Some still retain relatively clear rims, while others have softer outlines, as though loose rock had slid downward and partially covered their original shapes. Between the impact craters are elongated ridges, sloping terrain, and low-lying regions where darkness remains for longer periods. On a world without oceans, rain, or wind, this landscape was not shaped by the familiar processes found on Earth. It is the result of impacts, weak gravity, rotational motion, and the extremely slow movement of loose material over long spans of time. The neck between the two lobes is the most striking feature. It is far narrower than either end, making the entire structure appear fragile. But that impression of fragility comes largely from the way humans understand objects under Earth's gravity. A narrow stone bridge on our planet must support much of its own weight. On Donaldjohanson, everything weighs far less. Its weak gravity means that each mass of rock produces only a small pull, so the connecting region does not have to support the lobes in the same way that a structure on Earth would. The neck is not a bridge suspended between two worlds. It is material belonging to the entire body, lying within the combined gravitational field of both lobes. Rock in that region is pulled by the larger mass while also being influenced by the smaller one. The rotation of the entire object further changes the direction that loose particles experience as downward. From the images, scientists can reconstruct much of Donaldjohanson's shape, but not every region was observed with the same level of clarity. A flyby provides only the viewing angles allowed by the spacecraft's trajectory. Some regions received enough light to appear in detail. Others remained in shadow, were blocked by the lobe in front, or were seen only from an extremely oblique angle. As a result, the three-dimensional model of the object still contains some uncertainty. Its large-scale features, the two lobes, and the narrow neck are clearly recognizable, but the exact shapes of individual slopes or hidden regions may continue to be refined as the data is studied more carefully. This does not lessen the value of what Lucy observed. It simply reminds us that even when a spacecraft passes within about 1,000 kilometers of the surface, a small world can still preserve areas that were never directly seen. The bilobed shape also raises a larger question. Donaldjohanson may not be a single rock that slowly grew into a peanut-like form. Its two sections may once have been separate fragments created during the same larger collision. When a parent body is shattered, its fragments do not always fly away along completely separate paths. Some pieces may leave the impact region at high speed and enter different orbits. Others move more slowly, remain close together, and continue to feel one another's gravitational pull. The gravity of a rocky body several kilometers long is weak, but it is not zero. If two large fragments approach each other slowly enough, they do not need a powerful force to remain together. Their paths may gradually curve inward. The distance between them may narrow, and their surfaces may eventually meet at a speed far lower than that of the original collision that created them. That encounter would not necessarily have been violent. The two fragments may have touched gently enough to avoid breaking apart again. Loose rock on their surfaces shifted. Protruding sections were crushed, and scattered material gathered around the point of contact. Over time, that region became the neck connecting the two lobes seen by Lucy. This explanation fits the shape of Donaldjohanson, but it is not a piece of history that was directly recorded. No camera observed the moment when the two fragments came together. Scientists must work backward from what remains. The differences between the two lobes, the narrow connecting region, the age of the fragment family to which the object belongs, and models describing how small bodies can reassemble after collisions. It is also not yet possible to conclude that Donaldjohanson's entire interior is simply a loose pile of rubble. Its surface reveals a shape consistent with the joining of two large fragments, but its deeper internal structure has not been measured directly. Some regions may contain relatively solid blocks of rock, while others may hold much more loose material. The external images allow many inferences, but they cannot reveal the entire interior of the body. What is more certain is that Donaldjohanson does not have the form of a world rounded by gravity. Its two sections still preserve their differences, like two pages of a history that never completely merged. The larger lobe, the smaller lobe, and the narrow neck together suggest that the object we see today may be the result of both destruction and reassembly. A collision separated material from a parent body. Later, a much gentler encounter may have brought two large fragments back together. Destruction and formation do not always lie at completely opposite ends of a process. In the asteroid belt, the same history of collisions can cause one world to disappear and then create a new world from what remains. Lucy passed by for only a blur, because its images revealed a structure that has remained intact for millions of years. The two rocky masses are still joined. The neck remains between them. The craters continue to preserve the marks of later impacts, while the slopes keep changing almost imperceptibly under the influence of gravity and rotation. That shape was already unusual enough, But as scientists track the positions of the two lobes from one image to the next, they realized that Donaldjohanson was not rotating steadily around a single axis. Earth rotates around a relatively stable axis. Because of this, day and night return in a familiar rhythm. The sun rises from one side of the horizon, crosses the sky, and sets on the opposite side. Although the planet's axis is tilted relative to its orbit around the sun, the entire sphere still maintains a type of motion that can be predicted from hour to hour, season to season, and year to year. A rotational axis is not a real physical rod passing through a planet. It is simply an imaginary line used to describe the direction around which an object is turning. For Earth, that line passes close to the two poles. As the planet rotates, most of its surface moves in circles around that relatively stable direction. This stability can easily make us assume that every object in space must rotate in the same way. They may spin quickly or slowly, and they may be round or elongated, but it can seem as though every object only needs to find a line through itself and continue turning around it. However, this is true only when the rotation is compatible with the way mass is distributed inside the object. A nearly spherical planet has its mass spread relatively evenly around its center. But an elongated, flattened body, or one made of two connected sections, has several very different directions around which it can rotate. If it spins along its length, most of its mass remains fairly close to the axis. If it rotates around a direction crossing its width, the two ends may extend much farther outward. Each type of rotation creates a different balance between shape, mass, and motion. In mechanics, these balanced directions can be described with precise quantities and equations. But to visualize them, it is enough to imagine an object with three unequal dimensions, like a thick book or an elongated box. There are directions around which the object can rotate relatively smoothly. There are also directions where even a slight disturbance can cause it to begin tilting and wobbling. When an object rotates smoothly around one of the natural directions that matches its mass distribution, scientists call it principal axis rotation. In this state, the body maintains a relatively stable relationship with its rotational axis. Each point on the surface follows a regularly repeating path, and the overall motion does not include an additional large wobble. This does not mean the axis must remain completely fixed in space. Earth also experiences extremely slow changes in the direction of its axis over long periods. But over individual days and years, its motion remains stable enough for day and night to preserve their familiar rhythm. A small asteroid can rotate in a similar way. Even with an uneven shape, it may spin steadily around a balanced direction. When observed from far away, its brightness will rise and fall in a repeating cycle. After each rotation, the same part of the surface faces the observer again under nearly the same conditions. But not every object reaches such a state. After an impact, a rocky body may receive a push that knocks it away from a stable rotational direction. Two fragments that have recently joined together may also carry different motions from before they made contact. In that case, the entire object continues to rotate, but its body no longer turns neatly around a fixed axis within it. The difference can be imagined through three types of motion. In the first, an object rotates steadily around a stable direction. A marked point on its surface returns to almost exactly the same position after each rotation. In the second, the object continues spinning but also wobbles slightly around its axis, like a top beginning to tilt as it loses balance. The third is more complex. The object tumbles end over end while the orientation of its body continues to change. So no single axis fixed to the surface is enough to describe the entire motion. Donaldjohanson belongs to this more complex type. Its motion, however, is not random. The asteroid does not change direction unpredictably from one moment to the next. It still follows the same physical laws as every other object in space. Its cycles can be measured, its motion can be modeled, and the positions of its two lobes can be predicted when enough initial data is known. One concept that helps bring order to this motion is angular momentum. The term can be understood simply as the tendency of a rotating object to preserve its rotational motion. Once a rocky body has begun spinning through space, and no large external torque acts on it, its total rotational motion does not simply disappear. The overall direction of its angular momentum can remain relatively stable even while the body itself wobbles and tumbles around that direction. It is as though the entire motion still follows a general path, but the two-lobed shape is not fixed to it. The larger and smaller lobes continuously change the way they face into space, while the total rotational motion remains conserved. So saying that Donaldjohanson does not know how to rotate is only a suggestive image. In reality, it is rotating in a very specific way. The difference is that its motion cannot be described as one simple turn around an axis fixed within the body of the asteroid. In a steadily rotating object, an imaginary axis can be drawn through the body and remain in almost the same position relative to the surface. But for Donaldjohanson, that line is no longer sufficient. As the two lobes move, the object's longest direction continuously changes relative to the overall direction of rotation. A single imaginary axis seems to divide into several different lines, each able to describe only one part of the motion. This state can continue for a very long time because space contains almost no friction to bring it quickly to a stop. On Earth, a spinning top placed on a table loses energy through friction with the surface and the surrounding air. It begins to wobble more strongly before eventually falling over. An asteroid in a vacuum has no tabletop resisting its motion, and no surrounding atmosphere to remove energy in the same way. Even so, tumbling motion does not necessarily last forever. Tiny deformations inside the object, the shifting of loose rock, and weak effects from sunlight can gradually redistribute energy over millions of years. Eventually, some objects may move toward a more stable state of rotation, but the process is extremely slow, especially for a small, cold, and irregularly structured body. Donaldjohanson remains in a state where its past has not yet completely settled. The collision that created the fragments, the contact between the two rocky masses, and the changes that followed are still present in the way the entire object moves. Its shape does more than determine its appearance. That shape also takes part directly in the rhythm of its rotation. From Earth, astronomers had previously detected a cycle lasting about 10.5 days. The brightness rose and fell, then returned according to that rhythm. Had Donaldjohanson been rotating steadily around a single axis, that number might have described nearly all of its motion. But the consecutive images from Lucy showed that the two lobes did not return to the same orientation after only one such cycle. While the object completed one end-over-end tumble, its overall orientation was still slowly tilting through another rhythm. Donaldjohanson does not have only a 10.5-day rotation. Within that motion is another, slower rhythm lasting nearly a month. One end of Donaldjohanson slowly descends, passes around the underside, and gradually reappears on the opposite side. About 10.5 days later, the entire object completes one end-over-end tumble. If that were the only motion being observed, the asteroid might seem to be rotating in a very slow but still relatively simple cycle. Yet during those 10.5 days, the neck and the two rocky lobes do not maintain the same orientation they had at the beginning. The entire body has tilted in another direction. The larger lobe does not return to exactly its previous position, and the smaller section also appears at a new angle. One end-over-end tumble has been completed, but the peanut-shaped structure has not yet returned to its original orientation relative to the surrounding space. This is the sign that Donaldjohanson carries more than one rhythm of motion. The first rhythm is the end-over-end tumble lasting about 10.5 days. During this motion, the asteroid's two ends gradually exchange positions, as though the entire body were slowly rolling over itself. One end moves downward, passes around the hidden side, and gradually returns, while the other end makes the opposite journey. The second rhythm lasts longer, about 26.5 days. During that time, Donaldjohanson wobbles around the direction of its long axis. The long axis can be imagined as an invisible line extending from the end of the larger lobe through the neck and toward the farthest point of the smaller lobe. As the object wobbles around this direction, the neck and the two lobes slowly tilt back and forth instead of maintaining a fixed orientation. The two motions do not occur separately, with one stopping before the other begins. They happen at the same time. While one end is passing around the underside, the entire long axis continues to tilt. While the two lobes wobble sideways, the object is still completing its 10.5-day end-over-end tumble. For this reason, it is difficult to hold the entire motion in the mind through a single still image. One photograph may show Donaldjohanson with its larger lobe pointing upward. Another image taken later may show that lobe shifted to the side. But understanding the full movement requires following the way both rhythms overlap across many days. It can be compared to a spinning top that is not standing upright, but leaning. It continues to spin around itself, while the tip of its axis also traces a wider circle through space. Donaldjohanson carries two overlapping motions in a similar way, although its bilobed shape makes its path more complicated than that of a smoothly balanced top. With a spinning top on a table, we can see the body rotating rapidly, while its tilted axis slowly traces a circle. Donaldjohanson has no table, no point of support, and no absolute vertical direction. There is only the direction of its total rotational motion, which remains relatively stable, while the body continues tumbling and wobbling around it. Scientists call this state non-principal axis rotation. The term means that the object is not rotating steadily around one of the natural axes fixed to its shape. A more intuitive description is tumbling motion. The word tumbling does not mean that Donaldjohanson is moving out of control. The asteroid does not suddenly change direction or rotate in a completely random way. Its two rhythms can still be measured. The positions of its two lobes can still be reconstructed. With enough information about its initial state, its future motion can still be calculated according to the laws of physics. The complexity comes from the fact that no single cycle is enough to describe the object's complete orientation. After 10.5 days, Donaldjohanson completes one end-over-end tumble, but its 26.5-day wobble has not yet finished. After 26.5 days, the wobbling motion returns to a similar state, but the number of end-over-end tumbles completed during that time is not a perfect whole number. For the entire object to return to nearly the same orientation relative to space, the two cycles must combine over a longer period. This is also why observations from Earth before Lucy's flyby revealed only part of the motion. Donaldjohanson's brightness changed clearly enough to emphasize the 10.5-day rhythm. When its broader section faced the observer, the amount of reflected light increased. When its narrower section or a smaller angle turned toward Earth, the point of light became dimmer. The 26.5-day rhythm was more difficult to detect because it overlapped with the brightness changes produced by the end-over-end tumble. The angle of sunlight, Earth's viewing position, and the irregular shape of the surface all influenced the signal. The distant data still contain traces of the complex movement, but not enough to clearly separate each component. Lucy changed that by observing the object from close range and from a sequence of different angles. In the images, scientists were not limited to measuring its total brightness. They could directly track the relative positions of the larger lobe, the smaller lobe, and the neck. Each time Donaldjohanson turned, the outlines of its two sections changed in ways that could be compared with models of its motion. If the object had been rotating around only one fixed axis, a simple model would have been enough to reproduce the changing views. The same region of the surface would have returned after each rotation in a regular rhythm. But the data did not fit that explanation. After the model completed the 10.5-day cycle, the positions of the two lobes still did not match the actual images. Only when a second wobbling rhythm of about 26.5 days was added did the modeled views begin to align with the sequence recorded by Lucy. Images that had once been only separate slices now became traces of a motion unfolding across many days. The difference between Donaldjohanson and Earth is not simply whether their axes are tilted. Earth's rotational axis is tilted by about 23 degrees relative to the plane of its orbit, yet the planet still rotates steadily around that axis. If an imaginary line were drawn through the two poles, it would remain connected to the same regions of the surface during every rotation. On Donaldjohanson, no single line fixed within the body can fully describe the motion. As the rocky object tumbles end over end, its longest direction continues to wobble. A point at the end of the larger lobe does not merely travel around a fixed axis. It is also carried along a broader curved path, created by the second rhythm of motion. Viewed from a stationary position in space, the path of that point would not form a simple circle. Instead, it would trace a winding trajectory that repeats approximately, but does not return to exactly the same position after each 10.5-day cycle. Seen from above an imaginary direction, the larger lobe might appear to sweep through a broad circle. Viewed from the side, the same motion would look as though the object were continuously flipping end over end. Seen along the long axis, the neck and the two lobes would appear to sway back and forth, first leaning to one side and then shifting toward the other. No single viewing angle can tell the entire story. Only when these perspectives are placed beside one another does it become clear that Donaldjohanson carries two rhythms at once. This motion does not alter its orbit around the Sun on a 10.5-day or 26.5-day cycle. The asteroid continues circling the central star along an orbit that takes several years to complete. The two shorter periods describe only the way the body orientates itself while traveling along that much larger path. These can be understood as two different layers of motion. On the broadest scale, Donaldjohanson moves around the Sun alongside other objects in the main asteroid belt. Within that journey, the entire body is simultaneously tumbling end over end and wobbling around its long axis. All of these motions occur together, but across very different timescales. From far away, this complexity is reduced to a point of light that grows brighter and dimmer. No one can see one lobe descending or the neck tilting to the side. Only small changes in the arriving light reach Earth. From closer range, the two rhythms begin to take shape. The larger lobe passes through the illuminated region, gradually disappears, and then returns. The smaller lobe changes position relative to the object's horizon. The neck continually tilts at different angles. Shadows inside the craters also move along paths that do not repeat after one simple rotation. This is where the numbers begin to become an experience. 10.5 days is no longer merely a cycle written in the data. It is the time required for one end of the peanut-shaped world to pass underneath and return. 26.5 days is the slower rhythm that causes the entire structure to continue tilting throughout that motion. From far enough away, we might imagine two faint paths surrounding the object. One follows the end-over-end tumble. The other is broader, representing the wobble of the long axis. The two paths do not exist separately, but weave together into a single motion. From a distance, they are only two cycles that can be written as numbers. But from the surface, they would transform both the path of the Sun and the meaning of a day. If you were standing on a rocky slope near Donaldjohanson's neck, the horizon might not form a smooth, even curve like it does on a nearly spherical planet. One side would open into the vast darkness of space, while the opposite side would be filled by the other lobe, rising like an enormous mountain so close that it would seem almost like part of the sky. Depending on where you stood, that mass of rock could occupy a large portion of your view. Craters on the opposite surface would appear beneath low-angle sunlight, while long ridges would cast sharp bands of shadow. There would be no atmosphere to soften the boundary between light and darkness. Wherever sunlight reached, the surface could appear clearly defined, while the area behind a rocky ridge would quickly fall into deep black shadow. The sun would still move across the sky, but its path would not repeat in a simple way. Donaldjohanson completes an end-over-end tumble about every 10.5 days, while also wobbling around the direction of its long axis on a cycle of about 26.5 days. Because both motions occur at the same time, the orientation of the surface relative to the Sun changes in a way far more complex than the cycle of day and night on Earth. At one moment, the Sun might appear low near a ridge. It would then gradually rise, but instead of following exactly the same path during the next cycle, its position might shift in another direction. The end-over-end tumble would have brought the surface back to nearly the same orientation, but the slower wobble would still be incomplete. As a result, the next period of illumination would not necessarily produce the same sky as the one before it. This does not mean the Sun would move randomly. Its path would still be determined by the asteroid's calculable motion and its orbit around the central star. But for someone standing on the surface, the combination of the two cycles would make sunrise and sunset difficult to describe with one simple rhythm. On Earth, a day is tied to the planet's relatively steady rotation. After about 24 hours, the same location faces the Sun again in nearly the same way. Sunrise returns from a familiar region of the horizon, even though its exact position changes with the seasons. On Donaldjohanson, no single rotation is enough to determine when the entire sky returns to its previous state. After 10.5 days, a location on the surface may have completed most of an end-over-end tumble, but the wobbling orientation of the entire object will still be different. Only the combination of both rhythms, together with the asteroid's motion around the Sun, can bring the lighting back close to an earlier arrangement. This makes the meaning of a day much less clear. A day could be defined by one end-over-end tumble, by the time between two moments when the Sun returns to the same place in the sky, or by a longer cycle in which both motions nearly repeat. These definitions would not necessarily produce the same number. Shadows across the surface would change in much the same way. A rocky ridge might cast a long shadow over the slope below. As the object continued tumbling, that shadow would slowly move. But at the same time, the long axis would still be wobbling, changing the direction of the incoming light once again. The shadow would not simply sweep across the surface and return along the same path. On the next cycle, it might tilt sideways or cross a different region. Near the neck, these changes could be even more noticeable. One lobe might block part of the sunlight, reaching the connecting region, like an enormous mountain passing in front of the sunday. Depending on the position and angle of rotation, the shadow of one lobe could move across the other or cover part of the neck for a period of time. But because the three-dimensional shape of the hidden regions is not yet known with perfect accuracy, any description of a specific sunrise should be understood only as a possibility consistent with the motion model, not as a scene that has been directly observed. Even the meaning of downward would differ from our intuition on Earth. There is no large sphere here where every vertical direction points approximately toward one central point. Donaldjohanson consists of two lobes of different sizes joined by a narrow neck. Each section contributes to the overall gravitational pull of the object. If you stood on the larger lobe, the gravity from the mass directly beneath you might provide the strongest influence, but the smaller lobe would still exert a weak pull of its own. Near the neck, the effects from both sides could become more evenly balanced. A rock resting there would not be pulled only toward the center of one lobe. It would respond to the combined force produced by the object's entire shape. Rotation would alter that direction as well. When an object spins, material on its surface tends to be carried outward from the rotational axis. On Donaldjohanson, because the axis is not fixed to the body in a simple way, the effect of rotation also changes with location and over time. Scientists combine the gravitational pull of the two lobes with the influence of rotation to calculate a quantity known as effective gravity. This can be understood as the direction a small rock would actually experience as downward at a given location. That direction depends not only on where most of the mass is located, but also on how the entire asteroid is moving at that moment. Gravity, there is extremely weak. An object weighing tens of kilograms on Earth would exert only a tiny force on the surface of Donaldjohanson. If a person could stand there with the proper equipment, the body would feel almost none of the familiar sense of weight. Lifting one foot might be easy, but placing it back down in exactly the right location would require much more control. A cautious step would not necessarily send the person immediately away from the surface, but pushing too hard could create a significant speed compared with the asteroid's weak gravity. There would be no air to slow the motion, and the ground would not pull the body back down as quickly as it does on Earth. Every movement would therefore need to be extremely gentle, with tethers or another suitable support system. This would not make the surface chaotic. A rock could still remain at rest on a slope if the direction of effective gravity held it there and the incline was not steep enough to make it slide. Dust and loose debris could still collect in low areas. The difference is that ideas such as low, high, steep, and flat could not be determined from visible shape alone. A rocky slope that appears gentle in an image might actually be quite steep relative to the direction of effective gravity. In contrast, a surface that seems sharply tilted against the horizon might hold material relatively securely if the combined force presses it against the slope. This is why surface models cannot rely only on the outlines photographed by Lucy. They must also account for how mass is distributed and how the object is rotating. In this landscape, there would be no sound of rocks rolling through the air, no wind passing through the neck, and no echo returning from the opposite lobe. If a stone broke free from a slope and struck the surface, vibrations could travel through the solid material, but the surrounding space would remain completely silent. The sun would continue tracing a slow curve across the sky. A crater would gradually emerge from darkness. A rocky ridge would begin blocking light that had previously fallen across the neck. The opposite lobe would change its apparent height above the horizon as the entire object tumbled and wobbled in another direction. After 10.5 days, the landscape might return to something close to an earlier orientation, but the sky would still be shifted. After 26.5 days, the wobble would nearly complete, while the object would have passed through a non-whole number of end-over-end tumbles. There would be no clear boundary marking where one day had ended and the next had begun in the familiar sense. From the outside, this motion can be described with two numbers. On the surface, it becomes a changing path of sunlight, a migration of shadow, and a direction of downward that always depends on the shape and motion of the entire world. Donaldjohanson has been tumbling this way for a very long time. There is no atmosphere to slow it quickly, and no external surface creating friction like a spinning top on a table. But the vacuum is not the only reason this state has survived. The way the two lobes formed, and the energy they carried from the past, remain embedded in every cycle of motion today. To understand why Donaldjohanson has not yet returned to a stable rotational rhythm, we must go back to a time before the object had its peanut-like shape. About 155 million years ago, Donaldjohanson did not yet exist in its present bilobed form. There was no narrow neck between two rocky masses, no 10.5-day end-over-end tumble, and none of the cratered surface later seen by the Lucy spacecraft. But most of the material that would eventually form the asteroid had already existed for far longer, contained within a larger parent body in the main asteroid belt. The mineral grains inside that parent body may have formed during the earliest stages of the solar system. They appeared while dust and rock around the young sun were still colliding, joining together, and gradually building larger masses of material. Over time, some of the carbon-rich material gathered into the parent body, carrying ice, primitive minerals, and compounds preserved from that ancient cloud of matter. That body may have been far larger than Donaldjohanson is today. Its greater mass would have allowed it to retain heat more effectively, creating an internal environment very different from the cold, dry surface observed by Lucy. Energy left over from its original formation, together with heat released by radioactive elements in the ancient material, may have melted some of the ice inside. Liquid water moved through small fractures between the rocks and reacted with minerals, leaving chemical traces that would remain within the fragments created much later. But the history of the parent body was shaped by more than slow changes within its interior. It also traveled through a region filled with countless objects orbiting the sun along their own paths. Most of the time, enormous distances separated them. But over millions of years, gravity could gradually alter their orbits, occasionally bringing two bodies to the same place at the same time. Another object began approaching the parent body. No one was there to observe its path, and no surviving evidence allows its exact size or angle of approach to be reconstructed. All that remains is the result, an impact powerful enough that the original structure could no longer remain intact. In the vacuum of space, no explosion echoed outward. No sound wave traveled through the darkness. But where the two surfaces met, the rock experienced immense compression within an extremely brief moment. The energy of motion was transferred into the material and traveled through the interior as shock waves. Layers of rock were compressed, fractured, and then torn apart. The region closest to the impact suffered the greatest deformation. Some material was crushed into small fragments, while larger blocks were forced away from their original positions. Cracks spread deep into the parent body, intersecting and dividing the mass into many sections. Once the impact energy exceeded the ability of gravity and the strength of the rock to hold the structure together, the parent body ceased to exist as an intact world. This breakup did not resemble a glass object shattering into sharp, completely separate pieces. A celestial body is a complex mixture of solid rock, empty spaces, dust, and regions with different strengths. Some sections may have broken away as nearly intact blocks. Others were crushed into smaller pieces or continued colliding with one another as the cloud of debris began to expand. During the first moments, fragments moved in many directions. Some were launched fast enough to leave the impact region behind. They entered separate orbits around the sun and gradually spread into a family of objects sharing a common origin. Astronomers can recognize such families because their members retain certain similarities in their orbits, like traces left behind by a larger structure that has disappeared. Donaldjohanson is believed to belong to one of these fragment families. By studying the orbits of the family's members and simulating how they dispersed over time, scientists estimate that the major collision occurred about 155 million years ago. That number can easily create a misunderstanding. It does not mean that the rocks forming Donaldjohanson have existed for only 155 million years. The minerals inside may be almost as old as the solar system itself, having already existed for billions of years before the collision occurred. The 155 million year timespan marks only a change in the way that material was arranged. It can be compared to a house built from very ancient stones. The age of the house begins when those stones are assembled into a new structure, but each stone existed long before that moment. Donaldjohanson also carries these two layers of time. Its material is extremely ancient, while its present form is much younger. This distinction matters because an asteroid is not always an object preserved intact since the birth of the solar system. Some bodies seen today are products of repeated cycles of destruction and reformation. Primitive minerals may once have been buried deep inside a large body, then released, mixed with material from other layers, and finally reassembled into something smaller. When the parent body broke apart, regions that had previously been deep inside may have been carried close to the surface. Minerals that once interacted with liquid water now appeared on dry fragments of rock, continuing to orbit the sun through the vacuum of space. The chemical signatures within them do not tell the age of Donaldjohanson as a complete object. They tell the story of an earlier environment inside a world that no longer remains intact. The post-impact debris cloud did not expand evenly like a perfect sphere. Each fragment received a different speed and direction of motion. Blocks near the impact point may have been launched more forcefully, while regions farther away experienced only small changes in velocity. Some fragments continued colliding, breaking apart further or changing direction. Smaller pieces scattered more widely, while larger blocks may have remained near the original region for some time. The gravity of the parent body weakened as its structure came apart, but gravitational attraction did not completely disappear between individual fragments. Each rocky block still had mass and still exerted a very small pull on nearby objects. At great distances, that force was almost insignificant. But when two large blocks remained close together and did not move apart too quickly, their weak gravity could still alter their paths. Some fragments had enough speed to escape the group and never return. Others traveled only a short distance before their paths were deflected by nearby masses. They may have moved around a shared center of gravity for a short time, collided gently with other fragments, or gradually gathered into new structures. The destruction of the parent body therefore did more than create a collection of separate objects. It also began a period of rearrangement. Rocky fragments released from the old structure began seeking new states under the combined effects of velocity, collisions, and gravity. Within that field of debris, large blocks carried both irregular shapes and rotational motions of their own. One block may have been spinning in one direction, while another approached from a different angle. If they met too quickly, another collision would continue breaking the material apart. But if their relative speed was low enough, the two surfaces could make contact without causing both bodies to disintegrate again. This was a very different threshold from the original impact. The collision that destroyed the parent body required enough energy to overcome both the strength of the rock and the gravity holding the larger mass together. The encounter that created a new object needed to be gentler, allowing fragments to touch and then remain together. Donaldjohanson may have been born through both processes. The major collision supplied the fragments of material. Weak gravity and slower encounters afterward brought some of those fragments back together. Its present shape was therefore not produced in a single moment, but emerged as the next stage in a sequence of transformations that began when the parent body was shattered. The images recorded by Lucy cannot directly reveal what happened 155 million years ago. The spacecraft saw only the surviving result: two uneven lobes, a narrow neck, impact craters, and ancient minerals exposed across the surface. From these traces, together with the orbits of the asteroid family, scientists reconstruct a history whose details carry different levels of certainty. Some questions remain open. The exact size of the parent body is unknown. Donaldjohanson's original position within that structure also cannot be determined with complete confidence. Its two present-day lobes may have come from neighboring regions, or from very different parts of the parent body. But the broader picture still suggests that the object seen today was assembled from fragments left behind by a major breakup event. That event ended one world, but it did not erase its material. The rocks continued moving. Minerals that had once remained in darkness within the parent body were carried out into space. Large blocks traveled through clouds of dust and debris, carrying rotational energy and unstable trajectories with them. Destruction, then, was not the end. In the asteroid belt, the disappearance of one structure can provide the material for many others. A larger world was torn apart, but some of its pieces remained close enough to begin a new history. Among the fragments moving away from one another, two large blocks were still traveling slowly enough for their too weak gravity to begin drawing the distance between them closed once again. The two rocky fragments did not need to collide at high speed to become a single object. After the impact that shattered their parent body, they may have continued moving through the same field of debris, following nearby paths, and remaining separated by distances that were small compared with the immense scale of the asteroid belt. Each mass had its own gravity, but that attraction was extremely weak. A rocky fragment only a few kilometers across cannot pull distant objects toward it the way a large planet can. Yet once two masses are close enough and are not moving apart too quickly, even that slight attraction can begin to alter their paths. At first, the two fragments may have been rotating independently. One mass spun around its own direction, while the other carried a different rhythm of motion inherited from the collision. They did not necessarily share the same shape, size, or orientation. Each fragment was a surviving portion of the parent body, carrying motion transferred to it as the original structure came apart. At greater distances, the two masses followed almost separate paths, but as the distance between them narrowed, their mutual gravity began to matter. It did not pull the two objects directly into one another all at once. Instead, the slight attraction gently curved paths that had previously been almost straight, causing each mass to shift a little farther toward the other. If their relative speed was too high, their weak gravity could not hold them together. The two objects would pass one another or collide hard enough to break into even smaller fragments. But if their speed was low enough, the distance could continue to decrease. An encounter that might otherwise have been only a near miss could develop into a prolonged approach, with the two surfaces gradually drawing closer through several cycles of motion. There was no clear boundary marking the moment when they began to belong to the same system. From far away, they were simply two separate fragments. As they came closer, each mass began moving more noticeably under the influence of the other. The center of their motion was no longer located entirely within either fragment, but gradually became a shared point somewhere between them. During this stage, they may have orbited their common center of gravity for a short time, or approached each other along a curved path without completing a full orbit. The available data is not enough to determine every step precisely. What can be inferred from the final shape is that their last contact was probably far gentler than the earlier collision. The two surfaces gradually moved closer. Protruding regions may have touched first. Rock at the point of contact was compressed, but the energy was not sufficient to destroy both masses. Some of the more brittle sections may have been crushed. Dust and loose fragments were pushed aside, fell into open gaps, or slid into the region between the two bodies. Gentle contact does not mean that no deformation occurred. Even at low speed, both objects carried their own mass and motion. When they touched, some of that energy had to be transferred into the rock. Sharp edges may have broken away. Weaker areas of the surface may have collapsed inward. The fragments may also have slid a short distance against one another before their motion decreased enough for them to remain together. Under such weak gravity, the small fragments created at the point of contact would not necessarily have fallen in one simple direction. They were pulled by both masses, while also being influenced by the rotation of the newly formed system. Some of this material may have gathered between the two larger sections, partially filling the gaps and gradually forming the narrow neck observed by Lucy. The present-day neck may therefore not be an intact feature that originally belonged to either fragment. It may contain material from both sides, together with dust and rocky debris rearranged during contact. However, there is no direct information about the deep internal structure that would reveal the exact arrangement of each layer. What can be said with greater confidence is that the external shape is consistent with the joining of two large masses. From that moment onward, they no longer moved as independent objects. Their combined gravity, the contact region, and friction between their surfaces caused the two sections to begin sharing one overall motion. The larger and smaller lobes retained their individual shapes, but every change in the motion of one section affected the other. This formation process was very different from the collision that destroyed the parent body. The original impact carried enough energy to create deep fractures, scatter rock, and erase the earlier structure. The later encounter had to occur at the opposite end of the velocity scale. It needed to be gentle enough to prevent the masses from breaking apart again, yet close enough for their surfaces to touch and for gravity to keep them together. One destructive process created the fragments. A slower process of contact then used those same fragments to build a new structure. Donaldjohanson preserves evidence of both events. Its minerals and rocky masses came from the parent body, while its two-lobed shape belongs to a later period of reassembly. No recording exists of the moment when the two lobes touched. It is impossible to know which region made contact first, what their original angle was, or how long the settling process lasted. Scientists can only begin with the object's present shape, and then test which physical scenarios could have produced something like it. A single rocky body stretched by rotation would likely have a different form. A celestial object deeply deformed by an impact would also be unlikely to develop two clearly bulging sections with a narrow neck between them. By contrast, the low-speed joining of two large fragments provides a better match for what Lucy observed. Bilobed bodies are not entirely unfamiliar within the solar system. Several other comets and asteroids also have shapes made of two connected sections. This suggests that gentle reaccumulation may be more common than intuition would first suggest. In an environment of weak gravity, fragments do not need to strike one another violently to remain together. They only need to come close enough, slowly enough, and lose just enough of their relative motion. When the two masses first made contact, the new system was not necessarily in equilibrium. Each section carried its own rotation, while their approach added further motion around their shared center. Once joined, all of that movement did not simply disappear. It was transferred into the newly formed object, causing Donaldjohanson to begin rotating in a complex state. Some of the energy may have been dissipated as rocks were crushed and material shifted within the connecting region. But in the vacuum of space, there was no air to remove that motion quickly. After contact, the two lobes may still have vibrated slightly, shifted by very small amounts, and adjusted their orientation around their shared center of mass. Over time, the connecting region became more stable. Small fragments settled into lower locations within the combined gravitational field. Some of the empty spaces were partially filled. The contacting surfaces remained under weak but persistent compression, enough to hold the two masses together through countless orbits around the Sunday. The narrow neck did not need to support weight in the way a bridge does on Earth. Each lobe was pulled toward the other by only a very small force, while the entire object remained in free fall around the Sunday. There was no ground below pulling the two masses downward and causing them to break apart. Their combined gravity needed only to be strong enough to prevent them from separating again. The new shape, however, made the motion more complex. Its mass was not distributed evenly around a round center. One lobe was larger, the other smaller, and material was concentrated unevenly on opposite sides of the neck. As the system rotated, each section tended to preserve its own inertia, making a stable rotational state difficult to achieve immediately. At that time, Donaldjohanson may have looked very different from the slowly tumbling object observed by Lucy. Models suggest that its initial rotation was probably considerably faster. A higher speed would have made the effects of rotation across the surface stronger, changing both the direction of effective gravity and the locations where loose rocks could remain stable. During its earliest rotations, the rocky slopes may have been continually adjusting. Loose material slid toward the neck or into lower regions. Some smaller blocks may have escaped from the surface if the motion was fast enough, while others remained held by the object's combined gravity. The bilobed structure gradually stabilized, but its rotation continued to preserve the memory of the joining event. Lucy saw only the result after millions of years of change. The two rocky masses had remained together long enough for new craters to form across both lobes. The surface had undergone periods of material movement. Sunlight had continuously influenced the motion of the entire body. Yet beneath all the changes that followed, the fundamental shape remained. One larger lobe, one smaller lobe, and the narrow neck between them continued to preserve the moment when two fragments from the same parent body were brought back together. When those two fragments became one object, Donaldjohanson may have been rotating at least 10 times faster than it does today. Donaldjohanson now takes about 10.5 days to complete one end-over-end tumble. On a human timescale, that is an extremely slow motion. If observed for only a few hours, the two lobes would appear to barely change position. But when the object first formed from fragments of its parent body, an equivalent cycle may have taken only a small fraction of that time. Models suggest that Donaldjohanson may once have rotated at least 10 times faster than it does today. This does not mean scientists directly observed that ancient state. No images were taken hundreds of millions of years ago, and no instrument followed the entire process as the asteroid slowed down. This estimate is inferred from its shape, its present motion, the distribution of slopes across its surface, and models describing how a bilobed object can evolve over time. If it once moved about 10 times faster, an end-over-end tumble may have lasted close to 1 Earth day, or perhaps even less, depending on the exact state of motion. The two lobes would have continually exchanged positions in space. The narrow neck would have tilted through different orientations more quickly, while shadows across the rocky slopes would have swept over the surface in a rhythm very different from the one Lucy observed today. The source of that speed may lie within the formation of Donaldjohanson itself. After the collision that shattered the parent body, each large fragment carried its own motion. One mass may have been spinning as it traveled away from the impact region. The other would also have had its own velocity and direction of rotation, which did not necessarily match those of the first fragment. When the two pieces approached and made contact, those motions did not simply disappear. Some of the energy was transferred into the rock, crushing material or causing it to slide around the connecting region, but the rest remained within the overall motion of the new object. The two lobes began sharing a common center of mass, while the inertia of each section continued to influence the way the entire structure rotated. If the two masses approached along an off-center path, they would not merely have touched. They would also have carried motion around their shared center, like two objects passing one another, but being captured before they could fully separate. The motion of their approach could have been converted into rotation within the new system. The angle of contact, their relative velocity, and the original spin of each fragment all help determine the state that followed their joining. Donaldjohanson may therefore have begun its present existence with a fast and unstable rotational rhythm. Its asymmetrical shape prevented the rotational energy from being concentrated into one simple cycle around a single axis. Part of the motion appeared as end-over-end tumbling. Another part remained in the wobble around the long axis. Tiny vibrations and internal shifts may also have persisted during the early stage, when the connecting region had not yet fully settled. If the object were nearly spherical, its mass would be distributed more evenly around the center. But Donaldjohanson has one large lobe, one smaller lobe, and a narrow neck between them. Each section extends a different distance from the shared center of mass. When the entire structure rotates rapidly, those differences become more important. Regions farther from the overall direction of rotation experience a stronger tendency to move outward. On a large planet, gravity is usually strong enough to hold material firmly against the surface. On an asteroid only about 8 kilometers long, gravity is far weaker. Rotational speed can therefore play an important role in determining whether a rock remains still, begins to slide, or leaves its position. Imagine a small grain of rock resting on a slope of the larger lobe. Gravity pulls it toward the mass beneath it, while rotation introduces an additional tendency to carry it outward from the direction of rotation. The direction that the grain experiences as downward does not come from gravity alone. It is the combined result of all the influences acting at the same time. When Donaldjohanson rotated faster, the effect of its motion was stronger than it is today. Effective gravity in some regions may therefore have been weaker or tilted in a different direction. A rocky slope that now appears fairly steep may once have held material more securely under the earlier conditions. In contrast, a region that is relatively stable today may once have experienced a stronger tendency to carry loose debris outward. Near the neck, the situation would have been even more complex. Material there lay between the gravitational pulls of both lobes, while also moving around the shared center of mass. Depending on the speed and direction of rotation, the connecting region may have become a place where debris accumulated, or one where some material was more easily displaced. The shape observed today is the result of an extremely long period of change. so the present neck cannot reveal exactly how it evolved during every stage. If the speed was high enough, small loose particles on the surface may have been lifted slightly away from the slopes. They would not necessarily have escaped the asteroid entirely. A grain of rock could have left the surface, followed a short path around the object, and landed somewhere else. Other fragments may have slid across ridges, collected in lower regions, or remained trapped near the neck. These processes did not need to occur everywhere at once. Donaldjohanson is not a sphere with identical conditions across its entire surface. Every slope has a different incline. Each lobe contributes differently to the gravitational field. Regions near the shared center of mass experience different effects from those at the farthest ends of the object. The surface may therefore have been continually rearranging itself during the period of rapid rotation. Some regions lost loose material, exposing more solid rock beneath. Other areas received additional dust and debris. Craters may have been partially filled, while smaller ridges gradually lost some of their original sharpness. But Donaldjohanson did not continue rotating rapidly at the same rate forever. Its present motion shows that it has slowed considerably. As its speed decreased, the balance between gravity and the effects of rotation also changed. Material that had been stable under the earlier conditions would not necessarily have remained equally stable under the new ones. A region may once have experienced a strong outward influence that tilted the direction of effective gravity toward one side. As the object slowed, that influence weakened, and the downward direction shifted closer toward the mass inside the asteroid. Loose rock began responding to the change. Grains that had remained still for millions of years could begin sliding in a different direction, not because of a major earthquake, but because the meaning of downward had gradually changed. The slowing process did not necessarily occur at a steady rate. Donaldjohanson may have passed through periods when its speed changed more rapidly, followed by intervals when its motion remained nearly stable. Its shape, rotational orientation, distance from the sun, and the way its surface absorbed and released heat could all have influenced the rate of its evolution. Current models suggest that a significant portion of the slowdown may have occurred during the past 20 to 60 million years. This is still an immense period compared with human history, but it is much shorter than the age of the material making up the asteroid. Donaldjohanson may have existed for more than 100 million years before entering a period when its motion began changing more strongly toward the state seen today. Its decreasing rotational speed should not be imagined as a clock being turned down by the same amount each year. There is no continuous air resistance removing an equal amount of energy after every cycle. The process depends on extremely small effects that can change with the shape and orientation of the object. As Donaldjohanson gradually slowed, the rhythms experienced across its surface became longer. Hypothetical sunrises and sunsets occurred less frequently. A rocky region could remain illuminated for longer before moving into darkness. Temperature changes between sunlit and shadowed areas began unfolding according to a new rhythm. The neck, the two lobes, and the cratered slopes retained their overall shapes, but the way they passed through sunlight changed. During the period of rapid rotation, one lobe may have continually swept in front of the other. Later, the motion became so slow that each visible change required days to unfold. If silhouettes of Donaldjohanson from different periods were placed beside one another, its past orientations would appear closer together, representing faster cycles. As the sequence approached the present, the spacing between those silhouettes would gradually widen. The two lobes would still perform the same kind of complex tumbling motion, but they would require more time to move through each part of the cycle. What took away most of that speed? One obvious possibility is another collision. A smaller object striking from the right direction could slow the asteroid down, speed it up, or alter its axis. Collisions have continued to occur throughout the history of the main belt. The craters on Donaldjohanson are evidence that smaller fragments have repeatedly reached its surface. Yet a collision large enough to explain the entire slowdown may not have been necessary. A force can be too small to create a crater, fracture rock, or produce any noticeable effect during a single rotation, yet still cause a major change if it acts for long enough. Donaldjohanson has an asymmetrical shape. Each slope receives sunlight at a different angle. Some regions heat more quickly, while others remain in shadow for longer periods. As the surface absorbs energy and then radiates heat back into space, extremely small reaction forces appear in different directions. Over a single day, the effect would be almost impossible to detect. Even over 1 year, it would remain too weak to noticeably alter the motion of an 8-kilometer-long mass of rock. But Donaldjohanson has orbited the Sun for millions of years, receiving sunlight, absorbing heat, and releasing energy again during every journey. An influence that is extremely small, when repeated for long enough, is no longer small in the history of a world. No other celestial body needed to strike Donaldjohanson. A far gentler force has acted on it every day, coming from the Sunday. Sunlight reaches the surface of Donaldjohanson, but it does not stop there. Some of it is reflected back into space, while the rest is absorbed by the asteroid's dark rock. The surface warms slightly under the sun, stores that energy for a time, and then releases it as infrared radiation, a form of light invisible to the human eye that still carries energy. This process takes place across every illuminated rocky slope. A region facing directly toward the sun receives more energy. A tilted surface receives sunlight at a lower angle. Areas near the neck may be blocked by the opposite lobe, while higher ridges remain exposed to the light. As Donaldjohanson tumbles end over end and wobbles through different orientations, the pattern of warmer and colder regions across its surface also changes slowly. Over the course of a single day, this is simply the familiar exchange of energy between sunlight and rock. But light is not completely without force. Every particle of light carries a tiny amount of momentum. When light strikes a surface and is absorbed or redirected, some of that momentum is transferred to the object. The push from a single particle of light is far too small to feel. Even countless particles striking a rock together do not produce any obvious motion over a short period. Donaldjohanson is about 8 kilometers long and contains far more material than any object humans could move directly. Sunlight cannot noticeably slow its rotation in a day or even in a year. Space, however, gives this process something that human life rarely has in abundance: time measured in millions of years. When the surface absorbs solar energy, the rock does not hold that heat forever. The atoms inside begin moving slightly more vigorously, and the energy is gradually released back into space as thermal radiation. That outgoing radiation also carries momentum. As a result, every infrared photon leaving the surface produces an extremely small reaction force in the opposite direction. It can be compared to a person standing on ice and repeatedly throwing very light objects in one direction. Each throw would shift the body by an almost unnoticeable amount. But if the process were repeated countless times without friction holding the person in place, the final change could become much larger. On Donaldjohanson, there is no person throwing objects, only photons leaving rocky surfaces at different angles. If the asteroid were a perfect sphere with a uniform surface and received sunlight in a completely symmetrical way, many of these tiny reaction forces might nearly cancel one another out. One side would release heat in one direction, while the opposite side produced an almost equal effect in another. The total force might alter the orbit slightly, but it would not necessarily create a significant torque around the object's center. Donaldjohanson does not have that symmetry. It consists of a large lobe, a smaller lobe, and a narrow neck between them. Its slopes do not all face the same direction. Craters, ridges, and depressions cause sunlight to be absorbed differently from one region to another. Some surfaces heat quickly, while others retain warmth for longer before releasing their energy into space. Because of this irregular shape, the tiny reaction forces do not all pass through the object's center of mass. Thermal radiation, leaving a slope near the end of the larger lobe, may create a rotational effect in one direction. Another region on the smaller lobe may produce an opposing effect. but the strength of the push and its distance from the center are not exactly the same. The two influences do not cancel each other perfectly. The remaining imbalance acts like an extremely gentle twist. In physics, an influence that tends to make an object rotate faster, rotate more slowly, or change its orientation is called torque. On Donaldjohanson, the torque created by sunlight is far too weak to be seen during a single end-over-end tumble, but it continues to appear every time the surface receives sunlight and releases that energy again as heat. To understand why the location of a force matters, consider a door. If you push close to the hinges, the door moves very little. If you apply the same force near the far edge, it turns much more easily. What creates the motion is not only the strength of the force, but also the distance between the point where it acts and the axis of rotation. On this bilobed world, rocky slopes lie at different distances from the center of mass. A tiny reaction force, emerging from the far end of the larger lobe, may create a different twisting effect from a similar force near the neck. When all the forces across the entire surface are added together, a very small net torque may remain. This effect depends on more than the object's overall shape, surface roughness, heat absorption, and the timing of when each region releases energy can also change the result. A rocky surface may receive sunlight at one moment but retain the heat and release it later. By then, the object's orientation relative to the sun has shifted slightly. The direction of the reaction force is therefore no longer the same as it would have been if the energy had been released immediately. Because Donaldjohanson both tumbles and wobbles, its illumination pattern is especially complex. A slope may move from sunlight into shadow while the entire long axis continues to tilt. The neck may receive less energy because one lobe blocks the light. Other regions may remain illuminated for longer periods, depending on the object's orientation. All of these tiny effects accumulate across millions of rotations. Some forces accelerate the motion, some slow it down, and others may alter the direction of the rotational state. The final result depends on a delicate balance between shape, orientation, thermal properties, and the asteroid's orbit around the Sunday. Only after understanding the process through these extremely small reaction forces do we need its scientific name. The phenomenon in which sunlight and thermal radiation alter the rotation of a small celestial body is called the Yorp effect. The name is formed from the initials of the surnames of 4 scientists who helped develop the idea and its models. But the essence of the effect is not contained in the name. It is still the same simple process repeated countless times. Sunlight arrives, the surface absorbs energy, the rock radiates heat back into space, and each departing photon leaves behind an almost imperceptible reaction force. The Yorp effect does not always slow an asteroid's rotation. On another object, the arrangement of slopes and heated regions may produce torque in the same direction as the rotation, gradually increasing its speed. Some asteroids may spin so rapidly that loose material begins moving toward the equator, leaves the surface, or helps form a small moon. On other bodies, the torque acts in the opposite direction and lengthens the rotational period. The effect can also alter the tilt of the axis or drive an object into a new state of complex motion. Sunlight does not produce only one outcome. The shape of the object determines how it responds to energy from the Sunday. For Donaldjohanson, current models suggest that Yorp probably contributed to slowing its motion. The object may once have rotated at least 10 times faster than it does today, before entering a period of significant deceleration sometime during the past 20 to 60 million years. This is not a direct measurement taken over tens of millions of years. Humanity has observed Donaldjohanson during only a tiny fraction of that history. No one placed a clock beside the asteroid while it was still rotating rapidly and followed it until the present. The conclusion has been reconstructed from its current motion, surface shape, thermal models, and geological features consistent with an object whose rotational speed has changed. Yorp should therefore be understood as an explanation with a strong physical foundation, not as a complete history that has been directly observed. Smaller impacts or shifts of material within the asteroid may also have contributed to changes in its motion. But sunlight provides a mechanism persistent enough to produce a major difference without requiring another destructive collision. Each time Donaldjohanson completes part of its end-over-end tumble, another rocky slope moves into the sunlight. Its temperature rises. Energy is stored within the surface layer and then gradually escapes. The resulting reaction force is too weak to disturb even a single rock, but its total effect on the entire body still leaves an extremely small change in the motion. The next cycle unfolds in almost the same way, but not exactly. The asteroid has traveled farther along its orbit around the Sunday. Its wobble has brought the two lobes into a different orientation. The illuminated regions have changed, causing the distribution of reaction forces to differ slightly from before. Over 1 year, the individual changes are almost impossible to detect. Over 1 million years, they have been repeated through countless rotations. Over tens of millions of years, their accumulation may have stretched an end-over-end tumble from roughly 1 day to more than 10 days. There was no single moment when Donaldjohanson changed from rotating quickly to rotating slowly. There was no day when the entire surface suddenly became aware that its rhythm had changed. Each cycle became longer than the one before by an amount too small to distinguish during any brief periods spent on the surface. But when time is extended far enough, the difference becomes clear. Two silhouettes of the object during its rapid rotation phase would appear close together. Today, the larger lobe requires many days to pass through the same portion of its motion. Sunlight did not slow the asteroid with one powerful push. It simply continued acting, cycle after cycle, until the rotational rhythm became entirely different. That change is not limited to the numbers describing its periods. As the rotation slowed, the outward influence on surface material also weakened. The gravity of the two lobes began to play a relatively greater role in determining where loose rocks could remain at rest. A rock once held on a slope under the previous balance would now experience a slightly different downward direction. A region that had once been nearly level relative to effective gravity could become an incline. Dust grains that had remained still for a very long time would begin tending to move toward new locations. Sunlight, therefore, did not directly lift individual boulders out of craters. It first changed the motion of the entire celestial body. As the rotational rhythm changed, the map of forces across the surface changed with it. The landscape began responding to the new state through extremely slow episodes of sliding. Over time, outlines could soften, lower regions could collect additional material, and slopes could be rearranged. The nearly imperceptible push traveled from light into motion, and then from motion into the landscape. As the rotational rhythm slowed, it was not only the length of a day that changed. Across the entire surface, the direction that loose rock experienced as down also began to shift. A small rock resting on a slope of Donaldjohanson does not know whether the asteroid is rotating quickly or slowly. Nor does it know that one end-over-end tumble once took only a fraction of the time it does today. The rock simply responds to the combined forces acting on it at any given moment. If those forces hold it against the surface, it remains still. If the direction of the pull changes enough and the slope beneath it becomes too steep, it begins to slide. As the rotational rhythm of the entire asteroid changes, that combined force changes as well. The difference during a single rotation is extremely small, but over millions of years, it can transform a place that once held loose debris securely into a slope that is no longer as stable as before. On Earth, downward is generally understood as the direction toward the planet's center. Whether standing on a mountain, in a valley, or beside the ocean, gravity pulls everything toward nearly the same point deep below. Earth's nearly spherical shape and enormous mass make this understanding accurate enough for most of everyday life. Donaldjohanson is not so simple. It is not a sphere with mass distributed almost evenly around one center. A large lobe lies on one side, a smaller lobe on the other, with a narrow neck between them. Each section creates its own gravitational pull, and a rock on the surface must respond to the combined gravity of the entire structure. If the rock lies near the far end of the larger lobe, the mass directly beneath it may have the strongest influence, but the smaller lobe still pulls it slightly in another direction. If the rock lies near the neck, the attraction from the two lobes may become more evenly balanced, causing the downward direction to differ from a line perpendicular to the visible surface. Rotation makes the picture even more complex. When an object spins, regions farther from the direction of rotation tend to be carried outward. On Donaldjohanson, this effect is not strong enough to pull the entire surface away from the asteroid, but it can still weaken or redirect the force holding loose rocks on certain slopes. Scientists combine these two influences into the concept of effective gravity. This is the force a particle of rock actually responds to at a specific location after the gravity of the entire body and the effects of rotation are considered together. The direction of effective gravity is the direction the rock experiences as downward. For this reason, slopes on Donaldjohanson cannot be evaluated by sight alone. A surface that appears sharply tilted in an image may not be steep relative to effective gravity. Conversely, a region that looks fairly level may be significantly misaligned with the direction in which material naturally tends to fall. To understand the surface, the science team must begin with the three-dimensional model reconstructed from Lucy's images. They estimate how mass is distributed within the two lobes, calculate gravity at many points, and then add the asteroid's present rotational motion to the model. The result is a slope map that describes more than the shape of the rock. It also indicates where loose material is likely to remain stable and where it may tend to move. That map still contains some uncertainty. Lucy observed certain regions under favorable lighting and from several angles, allowing their contours to be reconstructed fairly clearly. Areas hidden in darkness, blocked from view, or seen only near the edge of an image are more difficult to describe with the same precision. If the shape of a slope remains uncertain, the calculated effective slope there will also have a larger margin of error. Even so, the clearly observed regions allow scientists to recognize an important pattern. When Donaldjohanson rotated faster in the past, the outward effect of its motion was stronger. The direction of effective gravity at that time was not exactly the same as it is today. Imagine a grain of rock resting on an inclined slope of the larger lobe. Gravity pulls it inward, while rotation produces a tendency to carry it outward in a different direction. Together, these influences create a combined force. If the surface is close enough to perpendicular to that force, the grain can remain in place, even though the slope appears quite steep in the three-dimensional shape. As the rotational rhythm slowed, the outward influence weakened. The gravity of the two lobes did not change very much, but the balance between the forces became different. The downward direction shifted closer toward the mass inside the asteroid. The rocky slope itself did not rotate independently from the body, but the way loose material experienced that slope changed. A place that had once been nearly level relative to effective gravity could become inclined. A grain that had remained stable for an extremely long time would begin to feel a force pulling it along the surface. If friction between the grain and the rock beneath it remained strong enough, it would stay in place. But once the pull exceeded the surface's ability to hold it, movement would begin. At first, it might be only a grain of dust shifting from its position. It could slide a few centimeters and stop behind a small ridge. Another stone might lose its support and roll slowly toward a lower region. These movements would not form a continuous flow like water, nor would they glow or spread rapidly like lava. Under weak gravity, rocks can move very differently than they do on Earth. A small stone may begin rolling but accelerate more slowly. When it strikes a ridge, it may bounce to a height greater than its own size, then follow a short arc before returning to the surface. Disturbed dust would not form a cloud suspended in the air because there is no atmosphere. Individual grains would simply follow their own paths under weak gravity before settling back onto the ground. One small movement could cause particles beneath it to lose their support, several more rocks might slide, after which the entire slope would become stable again. Thousands of years might pass before another change occurred in the same region. The landscape would not need a major event to continue rearranging itself. Slopes that had been stable under the faster rotational state did not all collapse at once as Donaldjohanson slowed. Its rotational rhythm did not change in a single moment. The direction of effective gravity shifted extremely gradually, and the surface responded in small episodes. Some regions adjusted earlier. Others remained unchanged for long periods before beginning to slide once their slopes crossed a threshold of stability. Material tended to leave steeper slopes and move toward lower regions within the new force field. Near the neck, depressions may have collected additional dust and small rocks from both sides. At the bottom of a crater, material from the inner walls may have accumulated into a thicker layer. Along high ridges, loose surface deposits may have gradually thinned, exposing stronger rock beneath. This process would not create an entirely new landscape in a short period. It would only adjust the features already present. A small ridge would become lower. A sharp slope would gradually soften. A depression would collect more material and become shallower than before. The bilobed shape also means that the same decrease in rotational speed produces different effects in different locations. The far end of the larger lobe lies at a different distance from the center of mass than the neck. The smaller lobe has its own curvature and slopes. A change in rotational rhythm may destabilize one slope while leaving another region almost unaffected. On a spherical body, simpler lines could be drawn to describe the effects of rotation. On Donaldjohanson, those lines bend around craters, rocky ridges, and the connecting region between the two lobes. Downward is not represented by the same arrow across the entire surface. Each location has its own arrow, and those arrows shifted as the rotational speed changed. The movement of material may also have influenced the rotation in return. When rocks shift from one region to another, the asteroid's mass distribution changes by a very small amount. On a large object, that difference might be insignificant. On a small, asymmetrical body, even minor changes can contribute to adjustments in its rotational state over long periods. Donaldjohanson was therefore not simply slowed by sunlight and then left unchanged. Its motion and terrain influenced one another. The rotational rhythm altered the way rocks experienced the slopes. Moving rocks changed the surface and the distribution of mass. The altered shape then continued to affect the way sunlight produced torque. This is a feedback cycle that unfolds far too slowly to be seen during a single flyby. Lucy captured only the state of the surface at one moment in time, but the features visible in its images may be the result of millions of years of interaction. Among sunlight, rotation, gravity, and loose material, not every softened feature on the surface can be attributed to one mechanism alone. Small impacts, expansion and contraction caused by temperature changes, and vibrations traveling through the object may also move rocks. Still, the changing direction of effective gravity provides a natural explanation for how many slopes may have been rearranged as the rotational rhythm slowed. There may never have been one landslide large enough to transform the entire asteroid. Instead, there were likely countless small movements scattered across immense spans of time. One rock rolled downward during one moment in geological history. A thin layer of dust shifted at another. Part of a crater wall lost its support and settled slightly lower. Each event was too small to become a dramatic moment. But the surface did not completely forget. Material left higher regions, accumulated in lower areas, and covered features that had existed before. Outlines that were once sharp gradually became more rounded. In Lucy's images, some craters no longer preserve the clear shape they had when they first formed. Their rims have become lower, their inner walls softer, and their floors may have collected additional material from the surrounding slopes. No rain has ever fallen there. No wind has carried dust across the surface, and no stream of water has flowed through the landscape. There is only extremely weak gravity, a changing rotational rhythm, and enough time for every grain of rock to seek a new position. Over millions of years, those small slides have been enough to alter outlines originally created by impacts far more powerful than the movements that later soften them. On Earth, the outline of a crater rarely remains unchanged forever. Rain falls along its walls, carrying soil and small rocks downward. Water flows through low-lying areas, ice expands inside cracks, and wind carries dust across surfaces that were once sharply defined. Over time, the slopes become lower, the crater floor fills in, and its original shape gradually blends into the surrounding landscape. Donaldjohanson has none of these processes. No clouds form above its two rocky lobes. No rain falls across the narrow neck. No rivers flow through its depressions, and no wind carries dust from the larger lobe to the smaller one. Its surface lies directly exposed to the vacuum of space, where material is influenced only by sunlight, temperature changes, impacts, weak gravity, and the rotation of the object itself. Yet in the images returned by Lucy, many craters no longer preserve the sharp appearance we might expect on a surface without weather. Some rims appear lower, the inner slopes seem softer. Small features around the edges have been covered or blended into the surrounding material, as though time had found another way to age the landscape. A newly formed crater usually leaves behind a relatively distinct structure. When a small rocky fragment strikes the surface, its energy compresses and forces material away from the impact point. Some of the rock is crushed into smaller pieces. Other material is thrown outward, creating a layer of debris around the rim. The crater rim rises above the nearby surface, while the inner walls slope down toward the newly formed floor. During the first moments, its outline may have been far sharper than anything Lucy sees today. Small ridges surrounded the rim. Blocks of rock were launched upward and fell back at different distances. A layer of dust and debris covered the inner slopes, but the overall form still preserved a clear record of the impact. The landscape then entered a quieter stage. No powerful force continuously reshaped the crater. Most of the time, everything may have remained almost motionless, but almost motionless does not mean completely unchanged. When Donaldjohanson rotated faster in the past, every rocky slope existed under a direction of effective gravity different from the one it experiences today. The gravity of the two lobes pulled material inward, while rotation added a tendency to carry it outward. A layer of loose rock on a crater wall may have remained stable because the combined forces held it against the slope in a relatively steady direction. As the rotational rhythms slowed, that balance shifted. The effect of rotation gradually weakened, while the gravity of the entire body became relatively more important. The crater wall did not immediately change shape, but the direction that material experienced as downward was no longer the same. A small rock resting on the slope might begin to feel a force pulling it along the surface. At first, friction would still hold it in place, but if it rested on a layer of loose material, even a slight change in the effective slope could cause it to slide a few centimeters. The rock would strike nearby grains, shifting them as well, before the entire group settled at a lower position. There would be no continuous flow. The entire crater wall would not collapse at once. Instead, movement would occur in separate episodes divided by immense spans of time. A few grains of dust might shift during one period. Another fragment might lose its support thousands of years later. A small part of the crater wall might settle lower as the material beneath it gradually found a new stable arrangement. Over time, loose rock would leave higher regions and accumulate on the crater floor. The layer of material there would slowly become thicker. Small depressions would fill first. Low ridges along the slopes would disappear beneath newly arrived dust and fragments. The crater floor would gradually rise, while the inner walls became less steep. The crater rim would not preserve its original height either. Rocks resting along the edge often occupy positions that are easily destabilized. If the direction of effective gravity changed, material could slide both inward and outward. Each movement would lower the rim by only a tiny amount, but after countless such events, the once sharp outline would gradually become more rounded. This is not erosion in the familiar earthly sense. No liquid cuts through the rock. No grains of sand are carried by wind and driven against the surface. The material is not removed from the region entirely. It is mainly rearranged within the same weak gravitational field. Higher areas gradually lose loose debris. Lower regions receive more material. A deep crater becomes shallower, not because rock has dissolved or been carried away, but because its walls slowly slide toward the floor. Extremely weak gravity gives this process a different rhythm from a landslide on Earth. A falling rock accelerates more slowly. When it strikes a lower slope, it may bounce upward, travel a short distance, and then touch the surface again. Small particles do not form clouds suspended in the air because there is no atmosphere. They simply follow short curved paths before the asteroid's gravity brings them back down. Some grains may cross a low ridge and settle in a neighboring region. Others may gather on the crater floor or inside gaps between larger rocks. Through many such movements, the surface gradually becomes smoother on a large scale, even though it remains rough and filled with sharp-edged material when viewed up close. Not every crater changes at the same rate. A crater near the far end of the larger lobe experiences a different force field from one located near the neck. The orientation of its slopes, its depth, the size of its particles, and the amount of loose material all affect its stability. Some regions may remain nearly unchanged for extremely long periods, while others experience many smaller episodes of movement. The regions seen most clearly by Lucy suggest that some craters have been softened considerably. However, the changing rotational rhythm should not be treated as the only explanation for every feature. An asteroid's surface also continues to experience smaller impacts over time. Each strike can send vibrations through the body, causing loosely settled grains to shift from their positions. Temperature changes may also contribute to the surface's long-term evolution. As a region moves from sunlight into shadow, the rock heats and then cools. Tiny cycles of expansion and contraction can gradually widen cracks. A large boulder may slowly break into smaller pieces, making material along the slopes more likely to move. But in the story of Donaldjohanson, its slowing rotation creates a special connection between the motion of the entire body and the shape of its landscape. Sunlight first changes the way the object rotates. That change shifts the direction of effective gravity. The surface then responds by moving material away from areas that are no longer stable and toward lower regions. In this way, a force that begins with sunlight can leave a trace along the outline of a crater, not by directly pushing individual stones, but by changing the state of the entire world beneath them. A crater forms within moments. Softening its outline may require millions of years. The two processes unfold on very different timescales. An impact arrives suddenly and leaves a clear mark. Then countless small changes begin slowly fading that mark. In a single image, we see only the result of both processes. The rim remains, proving that an object once struck the surface, but the slopes are lower, showing that material continued moving after the impact. The crater floor contains layers of debris that were not part of the original moment, but were added gradually over time. Each layer is extremely thin. One may consist only of small grains from part of the crater wall. Another may have arrived after a nearby impact, sent vibrations through the surface, and caused loose material to fall. These layers do not have distinct colors that can be counted like tree rings, but they still preserve the history of the surface through the way the particles are distributed. If the same crater could be observed over millions of years, the changes would probably be almost impossible to detect from one day to the next. A ridge would disappear too slowly, a slope would lower by too little. Only by placing its earliest state beside its final one would it become clear how far the landscape had changed. This is how Donaldjohanson grows old. Not through rain, wind, or seasons of melting ice. It ages through changes in rotational motion, through rocks sliding with extraordinary slowness, and through layers of loose material seeking more stable positions within a weak gravitational field. The craters remain, but they no longer look exactly as they did when they formed. Time has revised their outlines. Their slopes have been softened. Small details have been buried beneath material that came from the crater walls themselves. Lucy saw a surface that both preserves the past and continually reshapes it. Impacts wrote large circles into the landscape, while the slowing rotational rhythm gradually faded the lines. But the rocky debris records more than the way the surface has shifted. Within its mineral structure lies evidence of a substance that could hardly remain for long on the surface today: liquid water. Lucy did not see water flowing through a crack in the rocks of Donaldjohanson, nor did the spacecraft detect a reservoir of ice beneath the narrow neck or a thin mist surrounding the two lobes. On the surface today, sunlight falls directly onto dark rock, while the space above it is almost completely empty. What Lucy recorded was far more subtle. It was the way infrared light interacted with minerals on the surface. Within patterns of light and darkness beyond the range of human vision, scientists recognized signs that liquid water had once touched the material, making up this asteroid, long before Donaldjohanson acquired its present shape. Every mineral has its own structure. The atoms inside are bonded together in different ways, which means they do not absorb every wavelength of light equally. Some portions of the light are absorbed, while others are reflected or emitted back into space. When light from the surface is separated into many wavelengths, those regions of absorption form a distinctive pattern. It can be imagined as a faint signature left by the mineral within the light. Scientists call this record a spectrum. Lucy measured light, reflected from Donaldjohanson, across many wavelengths, including the infrared. When the data was compared with known minerals, the research team found signatures consistent with iron-rich clay minerals. The word clay may bring to mind soft earth along a riverbank or mud beneath a lake. But in planetary science, clay minerals do not necessarily have to form on a surface with rain, rivers, or oceans. They can develop deep inside a rocky body, where liquid water reacts with minerals already present. This process is generally known as aqueous alteration. Water does not simply pass through empty spaces and disappear without leaving a trace. It takes part in chemical reactions, changes the structure of the rock, and produces new minerals containing molecular groups associated with water. The signature, observed by Lucy, is therefore not an image of water that still exists. It is a chemical memory of a time when liquid water was once present. That time most likely did not belong to Donaldjohanson after its two lobes had joined together. An object only about 8 kilometers long has weak gravity and loses heat relatively quickly. Its present surface is exposed to vacuum, solar radiation, and large temperature differences between illuminated and shadowed regions. Liquid water would have difficulty surviving for long under such conditions. The origin of the clay minerals must be traced much farther back in history, to the larger parent body that once contained the material now forming Donaldjohanson. When the solar system was young, that parent body may have formed from rock, carbon-rich material, and ice trapped inside its pores. In the cold of space, the water did not initially need to exist as a liquid. It may have remained locked in ice, mixed among grains of dust and primitive minerals. As smaller fragments combined into a larger body, some of the energy from their collisions was retained inside. Radioactive elements present to the ancient material also decayed and released heat. Although each particle produced only a small amount of energy, the total heat inside a sufficiently large rocky body could build over long periods. If the temperature rose beyond the point at which ice began to melt under suitable conditions, liquid water appeared inside pores and fractures. There did not need to be a vast chamber of water or a hidden ocean. Thin films of water moving between grains of rock would have been enough for chemical reactions to begin. The water traveled through regions rich in primitive minerals, altering some of their original structures and creating clay minerals. Iron already present in the rock became incorporated into these new minerals, producing a composition that Lucy could indirectly recognize billions of years later. The entire process may have unfolded in darkness, deep beneath the surface of the parent body. No sunlight reached it. No flowing water carved a visible channel. There was only heat, porous rock, and water moving extremely slowly through narrow fractures. But that environment did not last forever. Internal heat gradually declined as the original radioactive elements decayed. Some of the water reacted with the rock and became bound within mineral structures. Other portions may have frozen again, escaped into space, or disappeared as the body underwent further changes. The signature of iron-rich clay suggests that water may have acted on the material for a relatively brief period compared with the aqueous histories of some other carbon-rich bodies. During the early stages of alteration, clay minerals can retain more iron. If water continues circulating and reacting with the rock for longer, the chemistry may progress further. Iron in some structures is gradually replaced to a greater extent by other elements, including magnesium. Donaldjohanson still displays signatures consistent with iron-rich clay minerals. This does not allow scientists to determine exactly how many years the water remained present, but it suggests that the alteration ended before the rock reached the more advanced level of transformation observed in some other objects. Water may have appeared, reacted with the minerals, and then disappeared relatively early. The environment lasted long enough to create clay, but not long enough to transform most of the material in the same direction. Even this apparent brevity must be understood on the timescale of a celestial body. It does not necessarily mean only days or years. A period considered short in geological history may still be extremely long compared with a human lifetime. What matters is that the process does not appear to have continued strongly throughout most of the parent body's existence. After the water disappeared or could no longer move freely, the minerals it had created remained within the rock. They survived deep inside for billions of years, preserving the chemical structures formed during that wetter period. Then the collision occurred. The parent body was shattered, and regions that had once been buried deep inside were carried outward. Blocks of rock containing clay minerals broke away from the original structure, moved through the field of debris, and became parts of new objects. Two large fragments later approached each other at low speed and joined to form Donaldjohanson. The narrow neck appeared. The larger and smaller lobes began sharing one overall motion. Minerals that had been altered by water in the darkness of the parent body now lay near the surface of a much smaller world. The millions of years that followed added other traces. Smaller objects formed craters. Loose rock slid down slopes as the rotational rhythm changed. Radiation and cycles of heating and cooling affected the outermost layer. But the chemical signature of water was not completely erased. When Lucy flew past, the spacecraft did not need to remove a rock sample from the surface to recognize this layer of history. Infrared light carried information from the minerals to its instruments. Small absorption features within the spectrum connected the present-day object to an environment that no longer exists. The data does not suggest that Donaldjohanson once had an ocean, nor does it show that rivers ever flowed between its two lobes or that liquid water remains hidden beneath the surface today. The bilobed shape formed only after the breakup about 155 million years ago, while the aqueous alteration most likely occurred far earlier. The traces of water, therefore, belong more to the material that forms Donaldjohanson than to its present landscape. They are memories inherited from the parent body, like ancient writing preserved within stones later used to build a new structure. This finding is also not evidence of life. Liquid water is an important component in many chemical reactions, but the presence of clay minerals alone is not enough to conclude that an environment could once have supported living organisms. The parent body may have been dark, cold at the surface, and contained only small pockets of water that existed temporarily within the rock. The value of this trace does not lie in transforming Donaldjohanson into a world that once resembled Earth. It shows that material in the asteroid belt experienced a more varied chemical history than its present cold and dry appearance suggests. A dark, rocky body may once have contained ice, Internal heat may have melted that ice. Liquid water may have moved through pores, altered minerals, and then disappeared. Later, a collision shattered the entire body, yet those chemical changes remain preserved within the individual fragments. Donaldjohanson, therefore, carries several layers of time at once. Its surface records relatively recent impacts. Its bilobe shape tells of reassembly after the parent body broke apart. Its tumbling motion preserves energy inherited from its formation, while the clay minerals carry the story back to a much earlier era, when water once moved through material inside a larger world that has since disappeared. Lucy encountered the asteroid for only a brief time, but the light collected from its surface passed through many layers of history. One part revealed its shape, another described its motion. The infrared portion uncovered traces of chemical reactions that occurred before Donaldjohanson was even born in its present form. Water was once present, but it did not remain long enough to alter the material more deeply. It moved through fractures in the rock, took part in slow reactions, and then became locked into minerals in another form. The liquid water disappeared, but the structures it helped create remained. Within the dark rock, tumbling through the main asteroid belt, part of that history continues to reflect sunlight, not as a visible stream of water, but as a tiny absorption pattern, just strong enough to reveal that this material once passed through a very different period. Two other asteroids also preserve traces of water, but water remained with them for longer, and their journeys carried them away from the main asteroid belt along very different paths. If Donaldjohanson, Bennu, and Ryugu were placed within the same frame, the first thing to stand out would be how similar their colors appear. All three are dark rocky bodies that reflect very little sunlight. Their surfaces are rich in carbon, rough in texture, and contain minerals showing that liquid water once moved through the material from which they formed during a very distant era. None of the three is the original parent body either. They formed from fragments left behind after larger objects were shattered by collisions. Ancient pieces of rock continued moving, encountered one another again under weak gravity, and reaccumulated into smaller asteroids. At first glance, the three objects seemed to tell the same story. Carbon-rich rock formed in the early solar system. Water once reacted with the minerals. A collision broke apart the parent body, and the remaining fragments came together to form a new world. But the more closely we look, the farther their histories begin to diverge. Donaldjohanson is the youngest of the three if age is measured from the time the rocky fragments reassembled into their present form. It emerged after a collision that occurred about 155 million years ago. The material inside it is far older, but the bilobed world observed by Lucy has existed for only a relatively brief portion of solar system history. Throughout that time, Donaldjohanson has remained within the main asteroid belt between Mars and Jupiter. It continues orbiting the Sun among a vast population of rocky bodies and has not been carried into a near-Earth orbit. Its shape is also distinctive. Two unequal lobes are connected by a narrow neck, making the object resemble a peanut from certain angles. The entire structure completes an end-over-end tumble in about 10.5 days, while simultaneously wobbling around its long axis on a cycle of roughly 26.5 days. This motion is extremely slow compared with those of the other two objects, but Donaldjohanson did not maintain this slow state from the moment it formed. It may once have rotated at least 10 times faster before the long-term influence of sunlight gradually slowed it down. The rock of Donaldjohanson also contains a subtler difference. Lucy detected signatures consistent with iron-rich clay minerals. These minerals show that liquid water once reacted with the rock inside the parent body, but the process probably ended relatively early. Water remained long enough to alter the minerals, but it may not have continued circulating for enough time to drive the chemistry much farther. A significant amount of iron remained within the clay structures, like a sign that the watery period ended before the alteration process reached the more advanced stage seen in some other bodies. Bennu tells a different story. It also formed from fragments of a larger carbon-rich body. However, The reaccumulation that created Bennu is thought to have occurred roughly 1 to 2 billion years ago. In terms of its present structure, it is many times older than Donaldjohanson. Bennu did not remain in the main belt. Over immense spans of time, small gravitational and thermal effects gradually altered its orbit. The object left the region between Mars and Jupiter and entered an orbit around the Sun that can bring it close to Earth's path. This migration did not happen through one sudden push. An asteroid's orbit can change extremely slowly under the influence of planets, gravitational resonances, and the way its surface absorbs and releases heat. Over millions of years, these small changes can move a rocky fragment from the main belt into near-Earth space. Bennu also rotates far more rapidly than Donaldjohanson. Instead of requiring more than 10 days to complete an end-over-end tumble, it finishes one rotation in about 4 hours. During a single Earth day, Bennu's surface passes through several cycles of light and darkness. Sunlight is believed to have contributed to Bennu's increasing rotational speed. The same Yorp effect that may have slowed Donaldjohanson appears to have produced the opposite outcome on Bennu. Its shape and the way its slopes release heat cause the total torque to act in the direction of acceleration rather than deceleration. This shows that sunlight does not impose the same fate on every asteroid. It produces only extremely small forces. The shape of each object determines how those forces combine. The traces of water on Bennu also point to deeper alteration. Magnesium-rich clay minerals suggest that water may have continued reacting with rock inside the parent body for a long period, perhaps millions of years. Compared with Donaldjohanson's iron-rich clays, this composition suggests an environment where water did not simply appear briefly, but remained long enough to continue transforming the material. Ryugu follows another historical path, though it shares more similarities with Bennu. It also formed from fragments of a carbon-rich parent body. The reaccumulated object seen today is thought to be older than Donaldjohanson, and after a long period, its orbit also carried it away from the main belt and into near-Earth space. Ryugu completes one rotation in about 7 hours. That rhythm is slower than Bennu's, but still far faster than Donaldjohanson's end-over-end tumble of more than 10 days. Sunlight may have helped drive it from a slower rotational state in the past toward the speed it has today. The minerals on Ryugu also indicate a prolonged period of aqueous alteration. Like Bennu, it contains clays richer in magnesium, consistent with a period during which water had more time to react with the rock. All three objects therefore preserve memories of water, but those memories are not the same. Within the material forming Donaldjohanson, water appears to have passed through during a relatively brief interval. Inside the parent bodies of Bennu and Ryugu, the process may have continued for longer, allowing chemical reactions to replace more of the iron with magnesium. This difference does not necessarily mean that one body simply contained more water than another. It may be related to when each body formed, the size of the parent body, how much internal heat it retained, the structure of its pores, or the region of the solar system where the original material accumulated. A larger parent body could retain heat for longer, allowing water to remain liquid. An object forming at a different time might contain different amounts of radioactive elements that generated heat. Material accumulating farther from or closer to the Sun may also have begun with different amounts of ice. From subtle differences in minerals, scientists can work backward toward events that occurred billions of years ago. The proportion of iron and magnesium in a layer of clay can become a clue to how long water remained present. A rotational period, lasting hours or days, can reveal how sunlight has influenced an object's shape. Its present orbit can indicate whether it remained near its birthplace or traveled through other regions. Donaldjohanson, Bennu, and Ryugu are not believed to be fragments from the same parent body. Their compositions and formation processes are simply similar enough to make comparison valuable. Each object resembles a different version of a common story, beginning under conditions that were not quite the same. Donaldjohanson remained in the main belt and gradually slowed beneath the influence of sunlight. Bennu and Ryugu left that region entered near-Earth orbits, and increased their rotational speeds. Donaldjohanson preserved iron-rich clay from a shorter period of contact with water. The other two carry magnesium-rich clay minerals, suggesting a longer period of alteration. Even their ages tell two kinds of time. The mineral grains inside all three may be extremely ancient, dating back nearly to the beginning of the solar system, but their present structures were rebuilt at different times. Bennu and Ryugu have existed as reaccumulated objects for roughly 1 to 2 billion years, while Donaldjohanson's bilobed world appeared only about 155 million years ago. Calling an asteroid ancient or young, therefore, always requires another question. Are we referring to the age of its minerals, the age of its parent body, or the age of its present structure? A clay grain may be billions of years old while resting today inside a much younger object. An asteroid may have been rebuilt relatively recently after a collision, even though every rock within it dates back to the youth of the solar system. When the three bodies are placed side by side, their similarities do not merge their stories into one. Instead, they make the smaller differences easier to recognize. All share the same dark appearance, but their thermal histories are not identical. All contain clay minerals, but water remained for different lengths of time. All were born from fragments, yet one remained in the main belt, while the other two traveled toward near-Earth orbits. These historical paths also show that the asteroid belt is not a motionless archive. Material can be shattered, reassembled, altered in its rotational rhythm, and eventually carried away from its original region. A rocky fragment may pass through many orbits before reaching the place where humans are able to observe it. Bennu and Ryugu came close enough for spacecraft to collect samples and return them to Earth. Donaldjohanson continues traveling through the main belt and was observed by Lucy only during a brief flyby. Yet even without a sample being brought into a laboratory, light from its surface allows the object to take part in the same comparison. Three dark rocky bodies stand within a single frame. Behind each one lies a different path. One remains between Mars and Jupiter. The other two gradually separate from the belt, extending toward near-Earth space. Those paths describe more than orbits. They carry the timing of formation, the history of collisions, rotational rhythms, internal heat, and the length of time water once remained present. Each small difference is a clue to where the material first formed, how it was heated, how long it encountered water, and which path eventually carried it into its present orbit. Lucy has long since passed by. After the moment of closest approach, the distance between the spacecraft and Donaldjohanson began increasing with every passing second. In the final images, the object no longer grew larger within the field of view. The craters disappeared first, followed by the ridges and slopes, which gradually blended together. The narrow neck was no longer clear enough to separate the two lobes, until the entire world shrank into a faint gray shape and finally returned to the point of light once observed from Earth. The spacecraft did not turn back. A flyby provides only one close encounter, and after that brief moment, Lucy continued along the trajectory calculated years before. Donaldjohanson remained behind, still traveling around the Sun through the vast space between Mars and Jupiter. But this time, that point of light was no longer as simple as it had once seemed. Within the data carried onward by Lucy was the shape of two rocky masses connected by a narrow neck, slopes preserving signs of material movement, and a rotational state more complex than anything that had ever been seen from a distance. The infrared observations revealed an even deeper layer of history, belonging to a time before the present object existed. That story did not begin on the day the two lobes touched. It began far earlier, within material that formed when the solar system was still young. Dust, rock, and carbon-rich compounds gathered into a larger parent body. Deep inside that ancient mass, heat may have melted some of the ice, allowing liquid water to move through narrow fractures and react with the minerals. The water left no visible riverbed or lakeshore. Instead, it changed the structure of the rock, creating iron-rich clay minerals before disappearing from its liquid state. Those new minerals remained in the darkness of the parent body, preserving the chemical record of a wetter period across spans of time longer than the entire history of humanity. Later, an impact powerful enough to break apart that structure occurred. The rock fractured, large masses separated, and smaller fragments spread into a cloud of material following many different paths. No explosion echoed through the vacuum, but the parent body could no longer preserve its former shape. Some of the material moved away and entered separate orbits. Other pieces remained close enough for their weak gravity to continue influencing their paths. Within that field of debris, two large masses may have approached each other at low speed. Their encounter did not repeat the violence of the original impact. It was gentle enough that the two surfaces were not shattered again. Material at the point of contact was compressed, crushed, and rearranged. Dust and rocky fragments filled the spaces between them. The connecting region gradually became a narrow neck, while the two larger sections retained their individual forms. One lobe was larger, the other smaller, and Donaldjohanson began to exist as a new structure built from extremely ancient material. When the two masses became one object, the motion they carried did not disappear. Each section already had its own velocity and rotational rhythm. Their off-center approach also added motion around their shared center of mass. All of that energy was distributed through an asymmetrical structure, meaning the newly formed body may have rotated far more rapidly than it does today. The two lobes continually changed direction. The neck moved through light and shadow on a much shorter rhythm. Loose rock on the surface experienced a stronger influence from the rotation, while the direction each slope experienced as downward was different from what it is today. Regions that held material securely under those conditions would not necessarily remain stable once the rotational rhythm began to change. Then an almost imperceptible influence began to accumulate. Sunlight struck the angled rocky surfaces. Some of it was reflected, while the rest was absorbed and later released back into space as heat. Each ray of radiation, leaving the surface, produced an extremely small reaction force. Because Donaldjohanson is asymmetrical, those forces did not completely cancel one another out. The remaining imbalance was not enough to alter the motion within a single day. It left no crater and could not make a boulder tremble. But sunlight continued arriving during every orbit around the Sunday. Over millions of years, that tiny torque was repeated countless times, helping to stretch the object's rotational rhythm into a much longer cycle. Donaldjohanson did not suddenly shift from fast rotation to slow rotation. There was no single moment dividing its history into a before and an after. Each cycle changed by only an extremely small amount. But when tens of millions of years are placed side by side, the difference becomes large enough that one end-over-end tumble now takes about 10.5 days. As the motion slowed, the landscape began to respond. The outward influence on surface material weakened, causing the direction of effective gravity on each slope to shift. A grain of rock that had remained still under the old balance could begin to feel a pull in a new direction. It might slide a few centimeters, come to rest, and leave another grain without support. These small movements did not form large flows. They were scattered across time, sometimes separated by thousands of years. Yet loose rock gradually left higher regions, accumulated in lower areas, and covered features that had existed before. The rim of a crater became lower. Its inner slopes grew less steep. Small ridges disappeared beneath thin layers of material, while the crater floor slowly rose. A feature created within moments by an impact began changing through movements spread across millions of years. No rain or wind took part in this process. No water flowed across the surface. The material was simply seeking stable positions within a force field that had changed. An influence beginning with sunlight entered the asteroid's rotation, and from its rotation passed into the shape of the landscape. Within each layer of rock, several periods of history therefore overlap. Minerals preserve evidence that water once existed inside the parent body. The bilobed shape carries the record of reassembly after the collision. The tumbling rhythm retains motion inherited from the formation process, while softened craters show that the surface continued changing afterward. No layer is completely separate from the others. An ancient mineral may lie within a stone that was knocked from its position by an impact and later slid to the floor of a crater as the rotational rhythm slowed. The same fragment of material can preserve traces of water, collisions, heat, and motion from different eras. This is why small size does not mean a simple life. Donaldjohanson is only about 8 kilometers long, yet its internal history includes repeated changes in shape and environment. Its material once lay inside a larger body, came into contact with water, was shattered, reassembled, and then continued evolving under sunlight. Even so, what humanity knows remains only part of the story. No recording exists of the collision that broke apart the parent body. No one watched the two lobes approach and touch. The slowdown across tens of millions of years was not measured from beginning to end. Even Donaldjohanson's internal structure has never been observed directly. We do not know exactly how much loose debris lies within the neck, how porous the two lobes are, or where the boundary between the original fragments may be located. Regions that Lucy did not observe from favorable angles also remain uncertain within the shape model. The history is reconstructed from several different pieces of evidence. Images reveal the outline and terrain. The changing positions of the two lobes over time reveal the motion. Infrared light provides clues about the minerals. Physical models test whether collisions, weak gravity, and thermal effects from the sun could produce the state now observed. Each conclusion, therefore, carries its own level of certainty. The two lobes and the tumbling motion are directly visible in the data. Clay minerals are identified through their spectral signatures. The ancient collision, the reassembly, and the slowdown are inferred from what remains rather than from direct observation of each event. This caution does not make the story any smaller. It keeps Donaldjohanson in its proper place between what is known and what remains open. A world can be understood with increasing clarity without every gap being filled by a claim of certainty. While the data continues to be analyzed on Earth, Lucy has already turned toward a more distant region. Donaldjohanson served as an important rehearsal before the spacecraft encounters the Trojan asteroids, objects that orbit the Sun near Jupiter's path and have never been observed at close range by a spacecraft. The first major Trojan encounter is planned with Eurybates and its small moon Quetta on the 12th of August 2027. After that, Lucy will continue toward other targets, revealing objects whose colors, compositions, and formation histories are not entirely alike. Those asteroids may preserve material from other regions of the early solar system, before the motion of the giant planets rearranged the orbits of countless small bodies. They may carry Lucy's journey into layers of history even older than Donaldjohanson's present form. But the bilobed world does not become less important simply because the spacecraft has moved on to its next destination. The brief encounter showed that even a target selected partly for testing can hold a scientific story of its own. An object once seen only as a point of light revealed how shape, sunlight, and time can work together to transform the motion of a world. Behind Lucy, Donaldjohanson continues orbiting the Sunday. One end slowly descends, passes beneath the body, and reappears in another direction. At the same time, the neck and the two lobes continue tilting through the longer wobbling rhythm. No spacecraft remains nearby to observe every change, but the motion continues as before. Sunlight continues striking the rocky slopes. The surface absorbs energy and radiates heat back into space. Tiny reaction forces continue to appear, even though none can be felt during any individual cycle. Loose rocks remain on the slopes, waiting for extremely slow changes in effective gravity to carry them toward another position. The encounter has ended, but the object's history has not. New craters may continue to appear. Old outlines may continue to soften. The rotational rhythm may keep changing in a direction that cannot yet be predicted with complete certainty. A force almost too small to feel has transformed the rhythm of this entire world, And even after the spacecraft has departed, that transformation is still continuing. One end of Donaldjohanson slowly moves downward. The other lobe gradually rises, while the entire two-part shape tilts in yet another direction. No sound travels through the surrounding space. There is no clear moment marking the beginning of a rotation, and no definite boundary showing that one has just ended. Every motion flows into the next. One end-over-end tumble takes about 10.5 days, but during that time, the neck and the two lobes continue wobbling through a longer rhythm. When one motion comes close to returning to its previous state, the other has not yet finished. This small world therefore never repeats itself in a simple way. Donaldjohanson has not truly forgotten how to rotate. That phrase only describes the impression it gives us when we see an object moving in an unfamiliar rhythm. It is not disoriented, nor does it move randomly. Every tilt, every end-over-end tumble, and every tiny change in orientation follows the same laws that have guided matter throughout the solar system since its earliest beginning. Its motion simply cannot be reduced to a single axis. It carries the shape of two rocky masses that once existed separately. It preserves the motion from the time those fragments approached, made contact, and became one structure. A larger lobe, a smaller lobe, and the neck between them leave the mass unevenly distributed. That shape takes part in every rotation, causing the entire body to tumble instead of spinning smoothly around one fixed direction. Its present motion also carries traces of an even more distant past. Before the two lobes joined, their material once belonged to a larger parent body. Water moved through narrow fractures inside that ancient rock, altered its minerals, and then disappeared from its liquid state. Later, a collision shattered the parent body and released its fragments into space. Those events ended long ago, but they have never completely left Donaldjohanson. The minerals still preserve the chemical signature of water. The shape still records the reassembly of the fragments. The motion still carries energy inherited from the formation process. Its craters and rocky slopes continue to preserve the changes that came afterward. Even the sunlight falling across the surface has become part of that history. Each region of rock absorbs a small amount of energy, warms, and then radiates heat back into space. Every ray of radiation that leaves produces a reaction force too small to be felt in a day, a year, or even across an entire human lifetime. But the lifetime of an asteroid is not measured in human years. When the same influence is repeated over millions of years, it can lengthen a rotational cycle, shift the direction of effective gravity, and cause material across the surface to seek new positions. A stone slides away from a slope. A thin layer of dust settles onto a crater floor. An outline that was once sharp becomes lower and more rounded. None of these changes needs to be large. They only need to continue. Lucy has left this region of space. The spacecraft is now heading toward more distant objects near the orbit of Jupiter, carrying data from an encounter that could happen only once. The distance between Lucy and Donaldjohanson continues to widen until the bilobed world is no longer a visible shape within its field of view. But the spacecraft's departure does not bring the processes on the asteroid to an end. Sunlight continues to arrive. The surface still passes through cycles of heating and cooling. Tiny reaction forces continue acting on its asymmetrical shape. Loose rocks remain on slopes that may one day no longer be as stable as they are now. Over the next millions of years, the rotational rhythm may continue to change. Donaldjohanson may move closer to a stable state, or new influences may make its motion complex in another way. A small impact may create another crater. A shift of material may slightly alter the distribution of mass. Sunlight will continue producing change without ever requiring a single dramatic moment. Perhaps this is the deepest lesson left by this small world. In the solar system, great transformations do not always begin with a powerful force. A push almost too small to detect, given enough time, can still change the way a celestial body rotates, the way rocks rest upon its slopes, and the way a landscape preserves the traces of its past. Within the vast asteroid belt, Donaldjohanson continues its journey around the Sunday. One end slowly descends. The neck tilts through the darkness. The lobe behind it appears again from a different angle, while sunlight silently passes across craters that have grown old. It is not completely stable, but it has never escaped the laws that have guided it since the first rocky fragments began drawing close to one another. Donaldjohanson continues tumbling through the darkness, and every slow rotation remains a piece of the past, still moving beneath the distant light of the Sunday.